Καλημέρα σας. Good morning to our distinguished guests. I will start, if our guests allow us, with some greetings in Greek at the beginning, and then we'll switch to English later on. We're very happy to have all of you here today. On the occasion of this symposium from electrons to elastic and electromagnetic waves in honor of Professor Οικονόμου's 85th birthday. You allow me now to switch in Greek. Κύριε Αντιπεριφερειάρχα, υπεύθυνε για τα θέματα διασύνδεσης με ερευνητικά και ακαδημαϊκά ιδρύματα, κύριε Δημοτικέ Σύμβουλοι του Δήμου και εκπρόσωπε του Δημάρχου Ηρακλείου, υπεύθυνε για τη διασύνδεση του Δήμου με πανεπιστημιακά ερευνητικά ιδρύματα, κύριε Πρίτανη του ΕΛΜΕΠΑ, κυρία Αντιπρίτανη του Πανεπιστημίου Κρήτης και εκπρόσωπε του Πριτάνεως, του κυρίου Κοντάκη, κύριε Πρόεδρε του ΙΤΕ, που είναι δυστυχώς για μας διασυνδεδεμένος στο ίντερνετ, και κύριε Διευθύνοντα του Ινστιτούτου Ηλεκτρονικής Δομής και Λέιζερ, κυρίες και κύριοι, είμαστε ιδιαίτερα χαρούμενοι που μετά από 5 χρόνια καθυστέρησης λόγω του κορονοϊού το 2020, που ετοιμάζαμε το αντίστοιχο meeting για τα 80 χρόνια του κυρίου Οικονόμου, πήγαμε πίσω 5 χρόνια και είμαστε έτοιμοι σήμερα να γιορτάσουμε. Και αυτό που θέλαμε όμως να κάνουμε είναι να προσκαλέσουμε διακεκριμένους επιστήμονες που θα μιλήσουν για τις βασικές αρχές και τις τρέχουσες εξελίξεις σε ερευνητικά θέματα με τα οποία ο κύριος Οικονόμου έχει ασχοληθεί κατά τη διάρκεια της ερευνητικής του πορείας. Θα προσπαθήσουμε να μην μιλήσουμε για την προσφορά του κυρίου Οικονόμου στο εκπαιδευτικό και ερευνητικό οικοσύστημα της Κρήτης, αλλά μόνο για το καθαρά επιστημονικό του έργο, το οποίο πολλές φορές κρύβεται πίσω από τη σημαντικότατη συνολική προσφορά του στο ΙΤΕ και στο Πανεπιστήμιο Κρήτης. Εδώ είναι η λίστα των διακεκριμένων ομιλητών που θα δείτε παρακάτω στο πρόγραμμα. Θα μιλήσουν με αντικείμενα ο καθηγητής Ping Seng, ο καθηγητής Martin Wegener, ο καθηγητής Sergei Bozenovli. If I pronounced it correctly, I apologize if I didn't. Probably I didn't. Ο καθηγητής Δημήτρης Χριστοδουλίδης και ο καθηγητής Θήμιος Καξίρας, ο οποίος μόλις έρχεται μάλλον από το Ρέθυμνο και η κίνηση στο δρόμο τον καθυστέρησε. Η ιδέα ήταν πριν από 5 χρόνια, όπως σας είπα, ήμουν ακόμα διευθυντής στο Ινστιτούτο και σε συνεργασία με τη Μαρία Καφεσάκη και τον Θήμη τον Καξίρα πήραμε την άδεια από τον κύριο Οικονόμου να οργανώσουμε αυτό το συμπόσιο και τα καταφέραμε σήμερα. Δεν θα πω πολλά πράγματα εγώ, 2 διαφάνειες ακόμα θα δείξω. Να πω ότι για την ερευνητική και παραγωγικότητα και απήχηση του έργου συνήθως χρησιμοποιούμε νούμερα, και αυτά τα νούμερα είναι για παράδειγμα αριθμός δημοσιεύσεων ή αυτό που λέγεται δείκτης H, Hirsch Index, υπάρχουν διάφορες δουλειές που αναλύουν και πώς πρέπει ακριβώς αυτά τα δεδομένα να χρησιμοποιούνται, και εδώ να πω ότι μια τελευταία δουλειά από τον κύριο Τζίτζικα, που είναι ερευνητής στο Ινστιτούτο Πληροφορικής του ΙΤΕ, έδειξε ότι αν λάβει υπόψη κανείς και τον αριθμό των συγγραφέων, και αφού αυτή η εργασία ανέλησε 300 προφίλ στο Google Scholar, έδειξε ότι ο κύριος Οικονόμου κατατάσσεται πρώτος στην παραγωγικότητα, σαν publication, σαν αριθμό συγγραφέων, όσο και στην απήχηση, H-index, σαν αριθμό συγγραφέων. Εδώ είναι από τον πίνακα που υπάρχει στο paper, αλλά έκλεισα τα άλλα ονόματα για να μην έχουμε ζήλιες. Έτσι, αλλά βλέπετε εδώ δείκτης H ανά αριθμό συγγραφέων και αριθμό δημοσιεύσεων ανά αριθμό συγγραφέων, που ο κύριος Οικονόμου είναι πρώτος και στις δύο κατηγορίες, παρά το ότι, ας πούμε, στη λίστα με απλά τον δείκτη H δεν φαίνεται να είναι τέτοια. Θυμίζω εδώ ότι για 20 χρόνια ήταν πρόεδρος του ΙΤΕ, οπότε αυτή η παραγωγικότητα είναι μέσα σε αυτή την τέτοια. Λοιπόν, θα ήθελα τώρα να προχωρήσουμε στους χαιρετισμούς. Θα ήθελα πρώτα να παρακαλέσω τον κύριο Ματαλιωτάκη, ο κύριος Γιώργος Ματαλιωτάκης, είναι αντιπεριφερειάρχης σχετικά με θέματα διασύνδεσης με ερευνητικά και ακαδημαϊκά ιδρύματα και εκπρόσωπος του Περιφερειάρχη Κρήτη, κυρίου Σταύρο Αναρτάκη.
Αξιότιμε κύριε καθηγητά, Ελευθέριο Οικονόμου, αξιότιμε πρόεδρε του ΙΤΕ, κύριε Χαρμανδάρη, κύριε Αντιπρόεδρε, κύριε Πλαξουσάκη, κύριε Πρίτανη, κύριε Αντιπρίτανη, αξιότιμοι προσκεκλημένοι, επιστήμονες και ερευνητές, αγαπητές κυρίες και αγαπητοί κύριοι, με ιδιαίτερη χαρά και τιμή, εκπροσωπώντας την Περιφέρεια Κρήτης και τον Περιφερειάρχη Σταύρο Αρναουτάκη, σας καλωσορίζω στο Επιστημονικό Συμπόσιο με θέμα «Από τα ηλεκτρόνια στα ελαστικά και στα ηλεκτρομαγνητικά κύματα» που διοργανώνει το Ίδρυμα Τεχνολογίας και Έρευνας. Σας καλωσορίζω ιδιαίτερα όσους επισκέφθηκαν το νησί μας από άλλες περιοχές της χώρας και από το εξωτερικό για να συμμετάσχουν στις εργασίες αυτού του σημαντικού συνεδρίου και σας εύχομαι καλή διαμονή. Η παρουσία σας μας τιμά ιδιαίτερα και έχει για μας διπλή σημασία. Καταρχάς, επιβεβαιώνει το υψηλό επιστημονικό επίπεδο των εργασιών του συμποσίου που θα ακολουθήσουν. Παράλληλα, υπογραμμίζει τη διεθνή εμβέλεια του έργου, προσέφερε στη μακρόχρονη επιστημονική του διαδρομή το τιμόμενο πρόσωπο, ο ομότιμος καθηγητής Ελευθέριος Οικονόμου. Θα μπορούσα να πω πολλά για τον καθηγητή Οικονόμου, αλλά είμαι βέβαιος ότι ως συνάδελφοί του γνωρίζετε καλύτερα. Γνωρίζετε καλύτερα και περισσότερα από μένα για τη συνεισφορά του στην επιστήμη της φυσικής. Επιτρέψτε μου όμως μία και μόνο επισήμανση. Το πλέον αξιοθαύμαστο που πέτυχε ο καθηγητής Οικονόμου μέσα από την κοπιώδη ενασχόλησή του με την επιστήμη, που είναι η κεφαλαιώδης προσφορά του στο νησί μας, την Κρήτη και συνολικά προς τη χώρα μας. Αρκεί να αναφέρω τον καθαριστικό του ρόλο ως προτεργάτη στη λειτουργία του Πανεπιστημίου Κρήτης, όπως και του Ιδρύματος Τεχνολογίας και Έρευνας. Αξιότιμοι κύριε καθηγητά, όλοι στην περιφέρεια Κρήτης είμαστε ευγνώμονες για όσα κάνατε. Σας ευχαριστώ όλους και εύχομαι κάθε επιτυχία στις εργασίες του συμποσίου.
Ευχαριστούμε πολύ κύριε Ματαλιωτάκη, κύριε Αντιπεριφερειάρχα. Θα ήθελα τώρα να περάσω στον κύριο Κονταράκη. Ο κύριος Κονταράκης είναι εντεταλμένος σύμβουλος του Δήμου Ηρακλείου για τη διασύνδεση του Δήμου με τα πανεπιστημιακά και ερευνητικά ιδρύματα και εκπρόσωπος του Δημάρχου Ηρακλείου, κύριου Καλοκαιρινού. Ο δικός μας ο Νίκος. Κύριε Κονταράκη.
Καλημέρα σας. Αξιότιμες κυρίες και αξιότιμοι κύριοι. Σας μεταφέρω το χαιρετισμό του Δημάρχου Αλέξη Καλοκαιρινού, που δυστυχώς δεν μπορούσε να παρευρεθεί σήμερα εδώ, παρότι το ήθελε. Από την άλλη πλευρά όμως, ακόμη κι αν ο Δήμαρχος ήταν εδώ, εγώ εδώ θα ήμουν, για να τιμήσω τον καθηγητή Ελευθέριο Οικονόμου, για τον οποίο τρέφω απεριόριστο θαυμασμό και εκτίμηση. Λόγω του ότι το πρώτο πτυχίο μου ήταν στη φυσική και το τμήμα φυσικής τότε ήταν σχετικά νέο και μικρό σε μέγεθος, γνώρισα όλους τους καθηγητές. Ο κύριος Οικονόμου ήταν η ψυχή του τμήματος. Σίγουρα και άλλοι καθηγητές του τμήματος προσέφεραν πολλά, αλλά το τμήμα θεμελιώθηκε και αναπτύχθηκε σωστά από τον κύριο Οικονόμου. Οι τομείς του τμήματος φέρουν τη σφραγίδα του. Οι εκλογές νέων καθηγητών φέρουν τη σφραγίδα του. Ακόμα και ο οδηγός πρωτοχειακών σπουδών του τμήματος φέρει τη σφραγίδα του. Σε αντίθεση με ό,τι γίνεται σε άλλα ελληνικά πανεπιστήμια, όπου κάθε καθηγητής θέλει το δικό του μάθημα να είναι υποχρεωτικό, εδώ υποχρεωτικά μαθήματα ήταν τα βασικά μαθήματα φυσικής και κανένα γενικό μάθημα δεν ήταν ιδιοκτησία κανενός. Ο κύριος Οικονόμου έγινε γνωστός παγκοσμίως για την έρευνά του και την παραγωγικότητά του σε αυτή. Αυτό όμως που χάραξε το όνομά του σε πέτρα, ώστε να μείνει ανεξίτηλο, ήταν η ίδρυση του ΙΤΕ και η στιβαρή διεύθυνσή του για πάνω από 20 χρόνια, αναδεικνύοντάς το με βάση διεθνείς αξιολογήσεις ως το καλύτερο ερευνητικό κέντρο της χώρας. Στους διαδρόμους του ΙΤΕ ήδη συζητείται η εποχή Οικονόμου και η μετά Οικονόμου εποχή. Κλείνοντας, θέλω να αναφερθώ στον κύριο Οικονόμου και ως δάσκαλο. Μου δίδαξε 3 μαθήματα φυσικής, θερμοδυναμική στατιστική φυσική, κβαντική δομή της ύλης και θέματα σύγχρονης φυσικής. Πήγα καλά στα 3. Λόγω του ενθουσιασμού για τη φυσική που μετέδιδε στις παραδόσεις του και λόγω της καθαρότητας της σκέψης του. Άλλαξα επάγγελμα και έγινα γιατρός, αλλά την καθαρότητα της σκέψης του προσπάθησα να τη μιμηθώ στη ζωή μου. Σε ευχαριστώ πολύ, δάσκαλε.
Ευχαριστούμε πολύ, κύριε Κονταράκη. Θα ήθελα τώρα, Ραφαήλ, να συνδεθούμε με τον πρόεδρο του ΙΤΕ, τον κύριο Βασίλη Χαρμανδάρη, διευθυντή της Κεντρικής Διεύθυνσης και πρόεδρο του ΙΤΕ. Δυστυχώς ο Βασίλης έπρεπε να είναι στο Παρίσι και είμαι σίγουρος, ξέρετε όλοι πόσο πολύ θα ήθελε να είναι εδώ. Βασίλη.
Ναι. Καλημέρα και από μένα, υποθέτω ότι με ακούτε. I will probably switch into English just because we have our visitors from abroad. It is a great pleasure and honor on behalf of the Central Administration of Forth to congratulate, first of all, Spiros Anastasiadis and Maria for organizing this very well-deserving event to honor Eleftheris Οικονόμου, a colleague at the University of Crete and one of the founders and the real soul behind the existence of the Foundation for Research and Technology Hellas. I will not get into the details of the work that Lefteris has done over the years. I'm sure there are other colleagues who can describe this much better. I would like to thank him, first of all, for the fact that he brought together a group of bright and ambitious young scientists from the other side of the Atlantic, some 40 years ago, who decided to leave their careers there and come to the great island of Crete in order to make happen something that was not possible up until that time in Greece. That is to establish a research institution which could make the dreams of other young scientists a reality and contribute to the advancement of science and scientific excellence, not only in Crete, but also in Greece, with substantive contributions also to the European scene. The fact that we are all here today is a testament that even bold dreams may become a reality against all odds, as Lefteris has reminded us over the years, and there are people in this room who have contributed substantially to the advancement of condensed matter physics, and not only. And thanks to the fact that the University of Crete and Forth are here. I would just like to remind to all of you that when we asked Lefteris some years ago whether he thought that this was a well-deserving endeavor and whether he was happy with where Forth is right now and the science that we produce, he actually said that he would be he was content, but he would have been much happier in his life if at some point the Nobel Prize in Physics would be awarded. So this actually is a testament to the fact that he keeps on putting pressure to all of us to continue working harder in order to actually advance science and contribute to society in the best way possible. Lefteri, thank you for actually helping us dream and move a bit further, a bit higher. I enjoy your workshop today, and I'm sorry I'm not there.
Thank you very much. We thank the president of the board of directors of Forth. Mike, the computer. Okay, so next I would like to ask Professor Maria Vamvakaki. Okay, switching Greek again. Ζητήσω από την κυρία Βαμβακάκη, καθηγήτρια του Τμήματος Επιστήμης και Μηχανικής Υλικών, αντιπρίτανη ακαδημαϊκών υποθέσεων, διαβίου μάθησης και ερευνητικής πολιτικής και εκπρόσωπο του πρίτανη του Πανεπιστημίου Κρήτης, κύριο Κοντάκη, που μαζί με το ΙΤΕ διοργανώνουμε την ημερίδα.
Αξιότιμη κύριε Οικονόμου, αξιότιμοι εκπρόσωποι των πολιτιακών αρχών, αξιότιμη κύριε Πρόεδρε, αξιότιμοι κύριε Πρίτανη, αξιότιμοι κύριοι Διευθυντές, αξιότιμοι προσκεκλημένοι, αγαπητές και αγαπητοί συνάδελφοι, αγαπητά μέλη της πανεπιστημιακής και ερευνητικής μας κοινότητας, κυρίες και κύριοι. Με ιδιαίτερη χαρά, τιμή και συγκίνηση, σας καλωσορίζω εκ μέρους της διοίκησης του Πανεπιστημίου Κρήτης στη σημερινή εκδήλωση για να τιμήσουμε έναν άνθρωπο και εξέχοντα επιστήμονα που πρωτοστάτησε στην ίδρυση και την εδραίωση του ακαδημαϊκού και ερευνητικού οικοσυστήματος της Κρήτης, υπηρετώντας το με ήθος, αφοσίωση και υψηλό επιστημονικό επίπεδο. Τον κύριο Ελευθέριο Οικονόμου, ομότιμο καθηγητή του Τμήματος Φυσικής του Κρήτης και διακεκριμένο μέλος και πρόεδρο επιτιμή του Ιδρύματος Τεχνολογίας και Έρευνας. Ο κύριος Οικονόμου αποτελεί μια πραγματικά ξεχωριστή προσωπικότητα στην ακαδημαϊκή και ερευνητική μας κοινότητα. Η σημερινή τελετή δεν αποτελεί απλώς μια τυπική εκδήλωση, αλλά μια έκφραση βαθύτατου σεβασμού και εκτίμησης για το επιστημονικό έργο, τη διδασκαλία, αλλά και τη συνολική προσφορά του κυρίου Οικονόμου στην ακαδημαϊκή κοινότητα της Κρήτης. Τιμούμε τον κύριο Οικονόμου σε αναγνώριση της ουσιαστικής του συνεισφοράς στη διαμόρφωση των πρώτων καθοριστικών βημάτων του Πανεπιστημίου Κρήτης, ως μέλος της ξεχωριστής εκείνης ομάδας των 5 Ελλήνων επιστημόνων από το εξωτερικό, οι οποίοι το θεμελίωσαν ως ένα πρωτοποριακό για την εποχή του Πανεπιστημιακό Ίδρυμα. Επιπλέον, τιμούμε την προσφορά του στο Τμήμα Φυσικής του Πανεπιστημίου Κρήτης, όπου υπήρξε ένας από τους 2 πρώτους καθηγητές και ο πρώτος πρόεδρος, συμβάλλοντας καθοριστικά στην εξέλιξή του στο κορυφαίο Τμήμα Φυσικής στην Ελλάδα. Επίσης, ο κύριος Οικονόμου ηγήθηκε της δημιουργίας του Ιδρύματος Τεχνολογίας και Έρευνας, το οποίο καθιερώθηκε ως ο κορυφαίος ερευνητικός οργανισμός της χώρας και απέκτησε διεθνή αναγνώριση για την αριστεία στην έρευνα. Επιπλέον, οραματίστηκε και ηγήθηκε της ίδρυσης του Τμήματος Επιστήμης και Μηχανικής Υλικών του Πανεπιστημίου Κρήτης, αποδεικνύοντας για μια ακόμη φορά τη διορατικότητα και το όραμά του. Ο κύριος Οικονόμου υπηρέτησε για πολλά χρόνια το Πανεπιστήμιο Κρήτης και το ΙΤΕ με ήθος, συνέπεια και βαθιά αγάπη για την επιστήμη και την εκπαίδευση. Από τη θέση του πρώτου Προέδρου του Τεχνικού Συμβουλίου, του καθηγητή και πρώτου Προέδρου του Τμήματος Φυσικής και του κοσμήτορα της Σχολής Θετικών και Τεχνολογικών Επιστημών, συνέβαλε ουσιαστικά στην πρόοδο του Ιδρύματός μας. Με το έργο του ενίσχυσε και ανέδειξε τη διδασκαλία, την έρευνα και τη στρατηγική ανάπτυξη του Πανεπιστημίου. Το ακαδημαϊκό του έργο, το οποίο περιλαμβάνει μεταξύ άλλων πολλά βιβλία θεωρητικής φυσικής και φυσικής συμπυκνωμένης ύλης στην ελληνική και αγγλική γλώσσα, ενέπνευσε πλήθος φοιτητών και συναδέλφων, οι οποίοι τον εκτιμούν βαθιά για το ήθος και τη σοβαρότητα με την οποία υπηρέτησε το έργο του όλα αυτά τα χρόνια. Δικαίως, επίσης, όλοι εμείς, ως φοιτητές του Πανεπιστημίου Κρήτης, τον γνωρίσαμε ως ο Θεός, χαρακτηρισμός ο οποίος υποδηλώνει ένα ακαδημαϊκό δάσκαλο αφοσιωμένο στο έργο του, που καθοδηγεί και εμπνέει τους φοιτητές του με ένα μοναδικό τρόπο. Η σημερινή τελετή είναι μια τιμητική αναγνώριση για την πολύπλευρη και σημαντική προσφορά του στα 2 ιδρύματα, αλλά και μια ευκαιρία να επαναβεβαιώσουμε τις αξίες της επιστημονικής αριστείας και της ακαδημαϊκής ελευθερίας. Αγαπητέ κύριε Οικονόμου, με την ιδιότητά μου ως αντιπρίτανης του Πανεπιστημίου Κρήτης, εκφράζω τη βαθιά ευγνωμοσύνη όλων των μελών της ακαδημαϊκής μας κοινότητας για τη μέχρι τώρα προσφορά σας στο ακαδημαϊκό οικοσύστημα της Κρήτης. Σας υποσχόμαστε ότι θα καταβάλουμε κάθε δυνατή προσπάθεια ώστε να σταθούμε αντάξιοι αυτής της σπουδαίας κληρονομιάς και των προσδοκιών σας. Σας ευχόμαστε υγεία, δύναμη και δημιουργικότητα για πολλά ακόμα χρόνια. Σας ευχαριστώ θερμά.
Ευχαριστούμε την κυρία Βαμβακάκη, την κυρία Πρίτανη. Τώρα εδώ κάτι άλλο βλέπω εγώ, από ό,τι βλέπει η οθόνη. Το είδατε ήδη προηγουμένως ότι ο επόμενος που θέλω να εισάγω είναι ο ερευνητής μας, διευθύνων του Ινστιτούτου Ηλεκτρονικής Δομής και Λέιζερ και αναπληρωτής διευθυντής στην προηγούμενη περίοδο, ο κύριος Εμμανουήλ Στρατάκης, ο οποίος δυστυχώς και αυτός βρίσκεται στην Αίγυπτο. Προσοχή εκεί. Και παρακαλώ, Μανώλη, να κάνεις το χαιρετισμό σου.
Thank you. Ευχαριστώ πολύ, Σπύρο. I will also switch in English because of our visitors. And dear esteemed guests, colleagues, and friends, I truly wish I could be with all of you there today, but even from a distance, it's a great pleasure and honor on behalf of the Institute of Electronic Structures and Lasers of Forth to join you in celebrating Professor Ελευθέριο Οικονόμου on the occasion of his 85th birthday anniversary. Professor Ελευθέριο Οικονόμου is not only the founder and the first president of Forth, but in many ways the heart and the driving force of our Institute of Electronic Structures and Lasers. And equally important for me, and I'm sure for many of you, someone I was privileged to have as a teacher. Professor Οικονόμου didn't build Forth and ISL for recognition or applause. On the contrary, he did it out of quiet commitment, a deep sense of purpose. As students, we didn't see him as professor. He was more like a guide and mentor. He had this calm and clear way of explaining things that somehow made the hardest concepts feel and seem doable. This is the reason that many of us, as mentioned by Professor Vambakaki, called him the God. Professor Οικονόμου was never one to seek the spotlight, but today we want to say with full hearts, thank you, Professor. Thanks for building Forth and ISL with heart and honesty. Thank you for teaching us with such care and generosity. Thank you for inspiring so many and for continuing to do so. Please join me in giving the biggest, warmest welcome to a remarkable teacher and inspiring leader, Professor Ελευθέριος Οικονόμου. Thank you.
Manoli, thank you very much.
Welcome.
We hope you all the best in the meeting you have in Egypt. As I mentioned at the beginning, the idea to organize this symposium back in 2020 came from Maria Kafesaki and myself and Professor Efthymios Kaxiras, who actually gave the international value to this event as well. And this year we have Kostas Makris with us in the organizers. So now I would like to ask Professor Kafesaki, professor of the... Oh, there it is. Okay, came back. Professor of the materials of the Department of Material Science and Engineering, and a former student of Professor Οικονόμου, to tell you some more about his works. So, Maria, yeah, I opened it, but it doesn't like me. It's okay, but it did it.
I will try to. Okay. Good morning. Good morning from me as well, and welcome. It's nice to see you all here, and it's nice to have our guests from abroad and so many friends and colleagues also in the Zoom. I would like to apologize to our non-Greek guests that I will talk in Greek as well, in order to be accessible from by the more general, let's say, audience. But my slides are in English, so you can follow what I'm going to tell. And okay, if you want to say something in English, I can say it afterwards. So I will give actually some, θα σας πω μερικά στοιχεία από το βιογραφικό του κυρίου Οικονόμου για να εισάγω με αυτά που θα ακολουθήσουν και εστιάζοντας, όπως είπε και ο Σπύρος, στο έργο του ως ερευνητής και λίγο σαν δάσκαλος. Ευτυχώς οι προηγούμενοι ομιλητές μου έκαναν λίγο το έργο μου λίγο πιο εύκολο, γιατί είπαν πολλά πράγματα από αυτά που ήθελα να πω για τον Οικονόμου σαν δάσκαλο. Λοιπόν, μιλώντας για το CV, όπως κάθε βιογραφικό, θα αρχίσω με τον Bachelor. Πήρε το πτυχίο του από το Εθνικό Μετσόβιο Πολυτεχνείο το 1963 και σαν ηλεκτρολόγος και μηχανολόγος μηχανικός. Τότε ήταν ένα τμήμα και μετά από μια στρατιωτική θητεία που τότε ήταν διαρκείας, πήγε στο Πανεπιστήμιο του Σικάγο, όπου πήρε το διδακτορικό του το 1969, πέρασε τα qualifying από ό,τι είδα από το βιογραφικό του και από ό,τι ξέρω σε χρόνο ρεκόρ και έγινε δεκτός για διδακτορικό σε θεωρητική φυσική συμπυκνωμένης ύλης και έχω γράψει εδώ το supervisor του και το ότι ήταν φοιτητής του ΚΙΤΕΛ, γιατί όλοι εμείς οι φυσικοί το ξέρουμε πολύ καλά από το διάσημο βιβλίο του. Εδώ είναι κάποιες φωτογραφίες της περίοδου αυτής. Μετά το Πανεπιστήμιο του Σικάγο, όπου έμεινε ως ερευνητής για ένα πολύ μικρό διάστημα, πήρε θέση το 1970 στο Πανεπιστήμιο της Βιρτζίνια σαν assistant professor στην αρχή και μετά και στη συνέχεια με προαγωγή σαν καθηγητής, όπου έμεινε περίπου 10 χρόνια, λίγο πάνω από 10 χρόνια. Τα τελευταία από αυτά τα χρόνια είχε την επιθυμία να γυρίσει στην Ελλάδα, οπότε ξεκίνησε με το Πανεπιστήμιο Αθηνών, όπου είχε πάρει μια θέση σαν καθηγητής στο τμήμα φυσικής. Από ό,τι ξέρω, απογοητεύτηκε κάπως από το τμήμα φυσικής στο Πανεπιστήμιο της Αθήνας, οπότε δέχτηκε την πρόταση να έρθει στο Πανεπιστήμιο Κρήτης, στο νεοειδρυθέν τότε τμήμα φυσικής του Πανεπιστημίου Κρήτης, όπου, όπως ήδη έχετε ακούσει, ήταν ο πρώτος πρόεδρος, από τους πρώτους καθηγητές, ο πρώτος πρόεδρος και ήταν αυτός που διαμόρφωσε σε μεγάλο βαθμό το πρόγραμμα σπουδών του τμήματος φυσικής. Στο τμήμα φυσικής είναι ακόμα και σήμερα, μετά τη συνταξιοδότησή του και εξακολουθώντας να διδάσκει μέχρι και πολύ πρόσφατα από τότε που εξελέγει. Και βέβαια το highlight της καριέρας του είναι η συνεισφορά του στην ίδρυση του ΙΤΕ, του οποίου είναι senior member και ιδρυτικό μέλος και ήταν και ο πρώτος πρόεδρος του ΙΤΕ, όπως ήδη έχετε ακούσει, για πάνω από 20 χρόνια. Πέρα από αυτές τις θέσεις που ήταν οι βασικές θέσεις, είχε διάφορες θέσεις σαν επισκέπτης, καθηγητής ή ερευνητής στο Πανεπιστήμιο του Σικάγο, της Λοζάνης, στο Πρίνστον, στο Iowa State, στο Δημόκριτο. Επίσης, είναι affiliated member, συνεργαζόμενο μέλος του Ames Lab στις Ηνωμένες Πολιτείες. Υπήρξε για αρκετά χρόνια σύμβουλος στην Exxon, που τότε είχε έτσι ισχυρό ερευνητικό προφίλ. Και βέβαια έχετε ήδη ακούσει, είπα δεν θα μιλήσω για το διοικητικό του έργο, για τις διοικητικές θέσεις του, αλλά χάρη πληρότητας και επειδή είναι τόσο σημαντικό για μας όλους, θα πρέπει να πω για τη θέση του ως ιδρυτικό μέλος του ΙΤΕ και σαν πρώτου Προέδρου από το 1983 για 20 χρόνια. Είχε έτσι μια θέση υψηλού πρεστίζ, ήταν Γενικός Γραμματέας Έρευνας και Τεχνολογίας για ένα χρόνο και επίσης Όπως μου είπε ο Σπύρος, μην ξεχάσεις να πεις, παρότι υπόθηκε ήδη, για την ίδρυση του Τμήματος Υλικών, του οποίου έχω τη χαρά και τη χαρά να είμαι μέλος. Είναι από τα ιδρυτικά μέλη, το βασικό ιδρυτικό μέλος του Τμήματος Υλικών. Επιστρέφω σε αυτή τη διαφάνεια και θα πω μερικά λόγια για την έρευνα σε κάθε μία από τις θέσεις αυτές που είχε, έτσι σε πολύ γενικές γραμμές. Ξεκινώντας από το Πανεπιστήμιο του Σικάγο, το ερευνητικό του αντικείμενο σε αυτή τη θέση ήταν η μελέτη των πλασμονίων σε μεταλλικές επιφάνειες. Τα πλασμόνια είναι ταλαντώσεις των ελεύθερων ηλεκτρονίων, τα λέω έτσι πολύ χοντρικά, ταλαντώσεις των ελεύθερων ηλεκτρονίων πάνω στην επιφάνεια του μετάλλου, οι οποίες μπορούν να διεγερθούν από ένα κατάλληλο, αν πέσει πάνω κατάλληλο φως, και μπορούν να φτιάξουν ένα επιφανειακό κύμα στην επιφάνεια του μετάλλου. Και αυτά τα επιφανειακά κύματα, επιφανειακά πλασμόνια συνδέονται, όπως θα δείτε σε μια από τις ομιλίες μας από τον κύριο Σεργέη Μποζεβόλνη, με εξαιρετικές τεχνολογικές εφαρμογές όσον αφορά ηλεκτρονικές διατάξεις. Αυτό εδώ είναι ένα paper από το διδακτορικό του κυρίου Οικονόμου και έχει μέχρι στιγμής πάνω από 1.700 αναφορές, αλλά αυτό που έχει ιδιαίτερη σημασία να δείτε είναι οι αναφορές στα συνάρτηση του χρόνου, ότι μέχρι το 2000 κάτι ήταν οι αναφορές ενός κανονικού paper. Μετά από το 2002-2003 εκτοξεύτηκε με την πρόοδο της νανοτεχνολογίας και με τις ιδέες γύρω από το θέμα των μεταηλικών. Οι άνθρωποι κατάλαβαν πώς μπορούν να ελέγξουν αυτά εδώ τα πλασμόνια και πώς μπορούν να τα διαμορφώσουν και να φτιάξουν πληθώρα διατάξεων. Οπότε αυτό το paper έγινε έτσι ένα must read, ας πούμε, θα έλεγα, στο πεδίο της πλασμονικής, που αποτελεί πλέον ένα ιδιαίτερο επιστημονικό κλάδο. Και όπως είπα, για πλασμόνια θα έχουμε την τιμή να έχουμε τον Σεργέη Μποζεβόλνη μαζί μας, που θα μας πει αργότερα. Πάμε στο Πανεπιστήμιο της Βιρτζίνια. Το βασικό ερευνητικό αντικείμενο αυτής της περίοδου, που ήταν τότε ένα θέμα που ήταν πολύ έτσι της μόδας, ήταν ηλεκτρόνια σε τυχαία συστήματα και σε συστήματα με ατέλειες. Και αυτό που εννοώ είναι ότι εδώ, ας πούμε, έχουμε ένα τέλειο κρίσταλο. Αν του βγάλουμε ηλεκτρόνια ή αν του βγάλουμε άτομα ή του μετακινήσουμε κάποια άτομα ή του βάλουμε ένα διαφορετικό άτομο, τότε φτιάχνουμε συστήματα με ατέλειες και με τυχαιότητα. Και ενώ τα ηλεκτρόνια σε αυτό το τέλειο κρίσταλο προχωράνε απρόσκοπτα, σε αυτόν εδώ πέρα ας πούμε ότι σκοντάφτουν στις τυχαιότητες, και αυτό έχει μεγάλη επίδραση στην αγωγημότητα του υλικού. Οπότε, διαμορφώνοντας κατάλληλα τις τυχαιότητες αυτές, μπορείς να διαμορφώσεις την αγωγημότητα του υλικού, κάτι που είναι επίσης έχει εξαιρετική απήχηση σε ηλεκτρονικές διατάξεις, σε ημιαγωγούς κλπ. Και ένα από τα θέματα που ασχολούνταν τότε ο κύριος Οικονόμου ήταν τι γίνεται αν έχουμε πάρα πολλές ατέλειες, που στην ουσία τα ηλεκτρόνια εντοπαγιδεύονται πάνω στις ατέλειες και έχουμε αυτό που λέμε Anderson localization και έχουμε μετάβαση υλικού από μέταλλο σε μονοτή. Εδώ είναι δύο από τα πιο σημαντικά άρθρα αυτής της περίοδου, που έχει γύρω στις 400 αναφορές το καθένα, αλλά το πιο, ας πούμε, highlight της περίοδου ήταν αυτό εδώ το βιβλίο, που έχει πάνω από 300 αναφορές και πραγματικά είναι ένα έτσι, πολύ, πολύ καλογραμμένο, πολύ σημαντικό βιβλίο στον τομέα του. Θυμάμαι όταν έκανα εγώ διδακτορικό που έκανα με τον κύριο Οικονόμου και με ρωτάγανε ποιος είναι ο supervisor σου και έλεγα Οικονόμου, ποιος μου λέγανε αυτό στο Green Functions. Wow! Οπότε είναι έτσι πολύ well known και έχει επανεκδοθεί. Επίσης, αυτό που θέλω να πω εδώ πέρα είναι να δείξω λίγο τα ονόματα στις δημοσίευσεις αυτές. Άρχισε και η συνεργασία τότε με τον Κώστα Σούκουλη, που ήταν επί χρόνια συνεργάτης και φίλος, συνεργασία ζωής, όπως λέμε. Τώρα, είχα πει να πω δύο λόγια για τα paper, αλλά θα τα προχωρήσω λίγο και θα μας... θα κλείσω λέγοντας ότι για μελέτη ηλεκτρονίων σε διάφορα στερεά συστήματα θα μας μιλήσει ο Ευθύμιος Καξίρας, που είναι και συνδιοργανωτής εδώ πέρα του συμποσίου, οπότε θα έχετε την ευκαιρία να ακούσετε αυτά τα θέματα, πώς έχει προχωρήσει η έρευνα σε ηλεκτρόνια και σε ηλεκτρονικές και σε κίνηση ηλεκτρονίων και ενέργειες ηλεκτρονίων σε υλικά. Τώρα, πάμε στο Πανεπιστήμιο Κρήτης. όπου ο κύριος Οικονόμου συνέχισε την έρευνα αυτή πάνω σε εντοπισμό Άντερσον και σε συστήματα με ατέλειες, αλλά επίσης ήρθε και ένα άλλο θέμα στο προσκήνιο. Έφυγε για ένα μέρος της δραστηριότητάς του από αυτά που λέμε κβαντικά κύματα, δηλαδή τα κύματα ηλεκτρονίων, και πήγε στα κλασικά κύματα. Και μια κατηγορία τέτοιων κλασικών κυμάτων είναι τα ακουστικά και τα ελαστικά κύματα. Οπότε το αντικείμενο της μελέτης ήταν ακουστικά και ελαστικά κύματα σε περιοδικά και τυχαία, κυρίως σε περιοδικά μέσα, αλλά και σε τυχαία. Ένα περιοδικό σύστημα όπου έχουμε διάδοση ακουστικών κυμάτων είναι κάτι τέτοιο, και το ενδιαφέρον ήταν να βρούμε συστήματα που έχουμε band gaps, δηλαδή που έχουμε περιοχές συχνοτήτων στις οποίες ο ήχος ή το σεισμικό κύμα δεν διαδίδεται, αλλά γυρνάει προς τα πίσω. Και η δουλειά που είχε κάνει τότε με τον Μιχάλη το Σιγάλα ήταν η πρώτη μελέτη, συνέπεσε με μια άλλη μελέτη κάποιων Γάλλων, η πρώτη μελέτη της δομής ζώνης, όπως λέμε, δηλαδή της μελέτης των επιτρεπτών και μη συχνοτήτων σε ένα υλικό, και η πρώτη πρόταση υλικού με φωτονικά χάσματα, με φωνονικά χάσματα, χάσματα δηλαδή με περιοχές όπου η διάδοση των ακουστικών κυμάτων απαγορεύεται. Για τέτοια υλικά, αυτά τα υλικά είναι και ένας προπομπός των ακουστικών μεταυλικών, που είναι ένα θέμα έτσι μεταγενέστερο, και για αυτά, για διάδοση ακουστικών κυμάτων, θα ακούσουμε την ομιλία από τον καθηγητή τον Bing Seng, που είναι από τους πρωτοπόρους στην έρευνα πάνω σε φωνονικούς κρυστάλλους και σε φωνονικά μεταυλικά. Και επίσης από τον καθηγητή Μάρτιν Βέγγενερ, που θα μας πει λίγο για ακουστικά μεταυλικά ή τον διάδοχο, ας πούμε, των φωνονικών κρυστάλλων. Τώρα, από τα τελευταία θέματα, στην δραστηριότητα του κυρίου Οικονόμου για πολλά χρόνια, για τα πολλά τελευταία χρόνια, ήταν η διάδοση ηλεκτρομαγνητικών κυμάτων σε μεταυλικά. Τα μεταυλικά είναι, εδώ βλέπετε κάποιες πρώτες δομές μεταυλικών, είναι κάποιες δομές που τις φτιάχνουμε στο εργαστήριο και μπορούμε να τις φτιάξουμε έτσι ώστε να έχουν ενδιαφέρουσες ιδιότητες, ασυνήθιστες και διαφορετικές από αυτές που έχουν τα συνηθισμένα υλικά, ή πολύ extreme, όπως λέμε, ιδιότητες. Και μία κατηγορία υλικών που ασχολήθηκε ο κύριος Οικονόμου ιδιαίτερα ήταν τα υλικά με αρνητικό δείκτη διάθλασης, και απλώς εδώ έχω βάλει μια εικόνα για να δείτε πόσο, ας πούμε, ασυνήθιστα μπορεί να είναι τα πράγματα αν έχουμε τέτοια υλικά. Εδώ είναι ένα ψάρι μέσα στο νερό, που, όπως ξέρετε, ίσως φαίνεται λίγο πιο πάνω λόγω της διάθλασης από την κανονική του θέση, και εδώ είναι πώς θα φαινόταν αν το νερό είχε αρνητικό δείκτη διάθλασης. Οπότε αυτά τα υλικά συνδέονται έτσι με πολλά ασυνήθιστα και ιδιαίτερα ενδιαφέροντα ηλεκτρομαγνητικά φαινόμενα, οπότε δούλεψε πολύ σε υλικά με αρνητικό δείκτη διάθλασης, σε υλικά που δουλεύουν στο οπτικό φάσμα, που χρειάζονται νανοτεχνολογία για να κατασκευαστούν, σε χειρόμορφα μεταυλικά, μελέτησε δυνάμεις Κασιμίρ σε μεταυλικά και πολλά και διαφορετικά άλλα φαινόμενα σε μεταυλικά. Δεν έβαλα κανένα paper εδώ, γιατί είναι πολλά papers τα οποία έχουν έτσι πολύ μεγάλο αριθμό αναφορών. Και εδώ πάλι όλη αυτή η δραστηριότητα ήταν σε στενή συνεργασία με τον Κώστα το Σούκουλη, που ήταν, ας πούμε, το τελευταίο κομμάτι της κοινής δραστηριότητας. Για μεταυλικά θα μας μιλήσει ο καθηγητής ο Μάρτιν Βέγγενερ από το Πανεπιστήμιο της Καλσρούη και από το Karlsruhe Institute of Technology. Και πάμε στο τελευταίο θέμα ερευνητικό, με το οποίο έχει ασχοληθεί σχετικά πρόσφατα σε συνεργασία με τον Κώστα το Μακρύ, που είναι ηλεκτρομαγνητικά κύματα σε μη ερμητιανά μέσα με ατέλειες ή σε μη ερμητιανά τυχαία μέσα. Μη ερμητιανά, λέγοντας εδώ, εννοούμε μέσα που έχουν κέρδος, δηλαδή είναι ενεργά υλικά, gain, όπως έχουμε στα λέιζερ, και απώλειες που συνδυάζουν κέρδος και απώλειες. Και αυτός ο συνδυασμός του κέρδους με την τυχαιότητα έχει ως αποτέλεσμα πολλά ενδιαφέροντα φαινόμενα, τα οποία ο κύριος Οικονόμου σε συνεργασία με τον κύριο Μακρύ προσπαθούν να μελετήσουν. Εδώ είναι το τελευταίο paper που βρήκα, το πιο πρόσφατο paper, και εδώ βλέπετε είναι κυματοδηγή και βλέπετε ότι το φως προχωράει σε ένα κυματοδηγό και μετά πηδάει ξαφνικά και πάει σε έναν άλλο κυματοδηγό, σαν αποτέλεσμα της αλληλεπίδρασης, της συνέργειας του κέρδους και της τυχαιότητας. Ένας από τους πρωτοπόρους στην έρευνα στα μη ερμητιανά συστήματα είναι ο καθηγητής ο κύριος Δημήτρης Χριστοδουλίδης από την Καλιφόρνια, ο οποίος θα μας μιλήσει. Η ομιλία του δεν είναι μάλλον σε μη ερημιτιανά συστήματα, αλλά έχει να κάνει και με θερμοδυναμική, που όπως ήδη ακούσατε από τον κύριο Κονταράκη, θερμοδυναμική είναι ένα από τα αγαπημένα θέματα του κυρίου Οικονόμου, έχει γράψει και σχετικό βιβλίο. Πέρα από αυτά τα θέματα που σας είπα, υπάρχουν και άλλα ερευνητικά θέματα που ήταν η έρευνα κράτησε λιγότερο χρόνο, δεν ήταν τόσο η χαρακτηριστική του συνεισφορά, όπως η περαγωγιμότητα, μαγνητικά υλικά, μη γραμμικά υλικά και πολλά άλλα θέματα υλικών. Θα πω και λίγα λόγια για τον Οικονόμου σαν δάσκαλο, βέβαια, αφού είχατε χαρά και την τιμή να τον έχω και καθηγητή μου. Δεν τον είχα τόσο στο αμφιθέατρο, νομίζω έχω παρακολουθήσει μόνο ένα μάθημά του σαν προπτυχιακή φοιτήτρια. Ακούσατε ήδη ότι το όνομά του ανάμεσα στους φοιτητές ήταν ο Θεός, και εγώ νομίζω ότι ο βασικός λόγος ήταν ότι φαινόταν να τα ξέρει όλα. Τουλάχιστον αυτή ήταν η εντύπωσή μας, εμάς τα ξέρει όλα. Δίδασκε, ήταν ενεργός δάσκαλος από τότε που ήρθε στο τμήμα φυσικής μέχρι και ίσως πέρυσι, νομίζω ότι φέτος ήταν η πρώτη χρονιά που δεν έκανε. Εδώ είναι τα βασικά μαθήματα που έχει διδάξει, αλλά έχει διδάξει και διάφορα άλλα. Όπως ήδη ακούσαμε, ήταν πρώτος πρόεδρος του τμήματος, όπως ήδη έχω πει. Και εδώ θα σας διαβάσω μόνο, είχαμε κάνει κάποτε με κάποιους συμφοιτητές μου και μαθητές του, τον είχαμε προτείνει για ένα βραβείο εξαίρετης πανεπιστημιακής διδασκαλίας, και θα σας διαβάσω τα επιχειρήματά μας, τέλος πάντων, για τα οποία άξιζε να πάρει το βραβείο. Τα γράφω και στα αγγλικά και στα ελληνικά. Το ένα ήταν το βάθος και το εύρος των γνώσεών του πάνω σε σχεδόν όλα τα θέματα της φυσικής, όχι μόνο σε φυσική στερεάς κατάστασης που ήταν η ειδικότητά του. Είχε βαθιά κατανόηση των θεμελιωδών αρχών που διέπουν τη φύση. Δηλαδή, είχε βαθιά κατανόηση της φυσικής, γι' αυτό και μπορούσε να απαντήσει στην ουσία κάθε ερώτηση, ή μπορούσε να βρει τη λύση σε κάθε θέμα, όπως ήταν η εντύπωση δικιά μου τότε. Επίσης, για τη γλαφυρότητα, την απλότητα, την καθαρότητα και τη σαφήνεια της διδασκαλίας του και την αφοσίωση στο διδακτικό έργο και το πάθος γι' αυτό. Του ταιριάζει πολύ ο χαρακτηρισμός, που δεν ξέρω αν είναι του ίδιου, ότι όσο πιο καλά τα ξέρεις, τόσο πιο απλά τα λες. Ήταν πραγματικά η ενσάρκωση αυτού του αποφθέγματος. Και το τελευταίο, πέρα από το ερευνητικό κομμάτι, ήταν η μεγάλη συγγραφική δραστηριότητα, κυρίως εκπαιδευτικών εγχειριδίων. Τα βιβλία του κυρίου Οικονόμου, οι πανεπιστημιακές εκδόσεις, ευχαριστούμε πολύ, μας έφεραν, έχουμε μία στο τραπέζι έξω, είναι τα βιβλία που έχει γράψει, που έχουν εκδοθεί από τις πανεπιστημιακές εκδόσεις, και ένα ακόμα, ένα αγγλικό, λείπει το Green's Function, αυτό το ιδιαίτερης απήχησης σύγγραμμα. Τώρα, μια και μιλάω για τα βιβλία, θέλω να ευχαριστήσω τις πανεπιστημιακές εκδόσεις τόσο που μας έφεραν τα βιβλία, όσο και που μας έφτιαξαν την αφίσα, ιδιαίτερα τον κύριο Βαρδάκη. Και αυτό είναι το τελευταίο μου slide, και είναι ο Οικονόμου σαν supervisor, κυρίως από τη δικιά μου οπτική, και αυτός είναι subtitle. Γιατί πραγματικά ήταν για εμάς τους φοιτητές του έπαιζε το ρόλο του ChatGPT. Ό,τι θέλαμε πηγαίναμε να τον ρωτάμε. Ένα πράγμα έτσι που μου έκανε εντύπωση, όχι τόσο στα φοιτητικά μου χρόνια, αλλά και αργότερα σαν συνεργάτης, ήταν ένα πράγμα που μου άρεσε, ήταν να παρακολουθώ τον τρόπο σκέψης του, και αυτό ήταν ένα πραγματικό μάθημα για μας τους φοιτητές του, τους μαθητές του, να παρακολουθούμε τον τρόπο που σκέφτεται, τον τρόπο που προσεγγίζει τα προβλήματα, τον τρόπο που λύνει τα προβλήματα, τον τρόπο που εξηγεί την επιστήμη, τον τρόπο που παρουσιάζει την επιστήμη. Όλα αυτά τα δίδαξε σε μένα και με το παράδειγμά του, αλλά και απευθείας, δηλαδή. Επίσης, σαν φοιτήτρια, εγώ πραγματικά είχα την εντύπωση ότι τα ξέρει όλα, γιατί ακόμα και αν δεν ήξερε κάτι, που προφανώς όταν κάνεις έρευνα αναπάντητα προβλήματα πας να λύσεις, δεν φαινόταν, ήξερε από πού να το πιάσει και από πού να ξεκινήσει, ας πούμε, για να βρει τη λύση. Δεν ήταν ποτέ χαμένος, τι είναι τώρα αυτό. Επίσης, ένα άλλο εντυπωσιακό ήταν ότι ενώ δεν ήξερε προγραμματισμό, μπορούσε να βρει λάθη. Του πήγαινε σε ένα αποτέλεσμα, ας πούμε, και σου έλεγε ότι μήπως, ας πούμε, έκανες αυτό το λάθος, μήπως διέρεσες με κάτι πολύ μικρό, μήπως δεν περίμενες τέτοια σχόλια από κάποιον που δεν ασχολείται με τον υπολογιστή και με τον προγραμματισμό. Και ένα μεγάλο ταλέντο που είχε, που πραγματικά το θαυμάζω και με αφήνει άφωνη, είναι το ταλέντο να βρίσκει φυσική εξήγηση. Νομίζω ότι μπορεί να βρει φυσική εξήγηση για τα πάντα. Δηλαδή, είναι πραγματικά εντυπωσιακό. Ένα εντυπωσιακό χάσμα που προφανώς πηγάζει από τη βαθιά γνώση της φυσικής και τη βαθιά κατανόηση των βασικών αρχών που διέπουν τη φύση. Και βέβαια θα πρέπει να πω εδώ πέρα, μια και μιλάω και για τη δικιά μου την εμπειρία, ότι πραγματικά ήταν πάντα διαθέσιμος, παρά το ότι εκείνη την περίοδο, ας πούμε την περίοδο του διδακτορικού μου, ήταν πρόεδρος του ΙΤΕ και είχε πολύ βαρύ διοικητικό έργο. Δεν θυμάμαι ποτέ να μου είπε έλα αργότερα. Αν πήγαινα στο γραφείο του και ήταν μόνος του, ας πούμε, δεν είχε κάποια συνάντηση, ήταν πάντα διαθέσιμος να μιλήσει, να εξηγήσει και να βοηθήσει. Και γι' αυτό πραγματικά αισθάνομαι τυχερή που τον είχα supervisor και ευγνώμων και ευχαριστώ πολύ.
Ευχαριστούμε πολύ, Μαρία. Τώρα νομίζω ότι θα περάσουμε στο επιστημονικό μέρος της ταινίας. Είμαστε μια ώρα περίπου πίσω. Εγώ, αν μου επιτρέπετε έτσι, να πω και εγώ ένα προσωπικό, έτσι, δεν θα ξαναμιλήσω σήμερα, έτσι. Να πω ότι και εγώ είμαι ευγνώμων στον κύριο Οικονόμου, όχι μόνο για όλα τα άλλα που ακούσατε εδώ, αλλά και γιατί νομίζω ότι αυτός ήταν ο σημαντικός παράγων που μου δόθηκε η ευκαιρία να είμαι στο τμήμα φυσικής. Έτσι, είδε ότι εκτός από την συμπυκνωμένη ύλη και αυτό που το λέμε soft condensed matter, χαλαρή συμπυκνωμένη ύλη, ότι και αυτό είναι μια περιοχή σημαντική. Και πραγματικά τον ευχαριστώ και εγώ, εκτός από όλα τα άλλα που ακούσαμε για το ΙΤΕ, αλλά και για το ξεκίνημα της προσωπικής μου καριέρας εδώ στην Κρήτη. Ευχαριστώ πάρα πολύ, κύριε Οικονόμου. Και νομίζω, είπα δεν θα ξαναμιλήσω, αλλά θα είμαι ο chair του επομένου session, οπότε απλά θα εισάγω τους ομιλητές. So now we can proceed with the scientific part of our symposium. And the first speaker is Professor Ping Zheng from Hong Kong University of Science and Technology in Hong Kong and more recently at Cambridge University in the UK. His talk is going to be on locally resonant mosaic plates. Professor Ping Zheng. So I don't know if you prefer this or that. I can use this. And this one should be... Maria, is this on? That's okay. Don't see any. I can use this. I can push this also. Okay. Don't matter. But yeah. Okay. Can people hear me? Yes. In fact, my talk will be divided into two parts mainly. So let me first say a few words. First of all, friends and colleagues, I'm honored to be invited to deliver this address today on the occasion of Eleftherios Economou's 85th birthday. Eleftherios is a friend whom I not only respect but admire very much for his multifaceted contribution to physics, as well as his very recognized leading role in establishment of Forth, which has trained many Greek and international students and postdocs, and now stands as one of the leading European research centers in physics. So I will first like to give a bit of background of Eleftherios. Then I will talk about the most recent research result that's very directly related to one of many Eleftherios' important contributions. Eleftherios, as Maria has already told you, in Greek,
He obtained his undergraduate diploma from University of Athens in 1963, and then directly went to University of Chicago, which is a renowned top research university for his graduate study. After getting the PhD degrees in 1969, he became an assistant professor in the University of Virginia, where he rose to the position of full professor in 1979. In 1981, at the prime of his professional career, Lefterius chose to leave the US to become the chair of theoretical physics at the University of Athens, and then subsequently a professor of physics at the University of Crete. At the same time, he led the effort that resulted in the creation of Forth. And with such a step, in hindsight, Lefterius has shaped and influenced the development of condensed matter physics in Greece during the last quarter of the 20th century. And from this perspective, I can say that Lefterius is one of the most influential physicists in Greece and Europe during this period. I got to know Lefterius initially through his publication on Hubbard model. I don't know why I got interested, I forgot. But when I heard one of his talks, I was very much impressed by the clarity of his presentation, as well as the persuasiveness of his arguments. I remember then when I heard that he will leave the University of Virginia to go back to Greece, I was surprised and also very much impressed, probably because of my somewhat similar background. As we all know, anybody leaving a full professor position in the US at the prime of the career usually pay a dear price. In terms of international reputation, prizes, and so on, because the US academic network will inevitably be broken. And the US academic network is one of the most powerful in the world. I asked to have a short meeting with Lefterius before he went back to Greece. I don't know if you remember this. When you were in New York, I think. And during the meeting, he essentially mentioned that Greece needs him, and he felt obliged to go. In looking back now, it is clear that Lefterius has a much grander plan in his mind at the time, but he probably felt premature to mention that. After he returned to Greece, I was invited multiple times to Crete to give talks and to participate in organized conferences. In fact, I first met Maria during one of such conferences. Lefterius made many contributions, but the one in particular stood out, and that was his pioneering role in phononic crystals in the early 1990s. As we all know, phononic and photonic crystals are forerunners of acoustic and electromagnetic metamaterials, in the sense of having used geometric structures to manipulate the functionality of classical waves. And today, my technical talk will be on the topic very much related to Lefterius phononic crystal contributions. So let me begin. So the technical talk's title is called a locally resonant mosaic plate. Is on some very recent results. So this work has been done in collaboration with my former student, now a postdoc at UPB in Spain, Vincent Romero Garcia, also at the UPB Spain, and Jean-Philippe Groby, and Le Mans, France. So when I mentioned is very much related, I refer to Lefterius' publication in 1992 that was very highly cited, where he showed the acoustic waves in a host with density that's higher, much higher than that of the spherical inclusions can result in a very big band gap. So but you can see the band gap is over at the finite frequencies. So the question in all the subsequent years is that can there be a zero frequency band gap? And what do I mean by that? So it means that can you have a band gap that starts at 0 plus frequency, namely a band gap that does not include zero frequency, because zero frequency represents the rigid motions of the system overall. So you don't want that to be missed. But instead, you start from 0 plus to a finite frequency. But that is generally regarded as impossible for the brass scattering mechanism from periodicity, because it requires an infinite or very large lattice constant. For other mechanisms, you can still have objections to the realization of zero frequency band gap, because theoretically there is a very influential body of theory based on so-called harmonization, which is the basis of effective medium theory, which essentially said every system, composite or disordered system, must have low frequency, long wavelength excitations. And in such a limit, the physical parameter of such excitations can be derived from the effective medium or homogenization theory. So if you can have a zero frequency band gap, then it would present a challenge to the effective medium or homogenization theory. So in 2002, I think, 2002, there was a publication in the Proceeding of Royal Society A by an Australian group, I think is by McFadden and his collaborators, in which they showed in an analytic solution, mathematical solution, in which if you have a perforated plate, in which you have the holes, periodic array of holes, with the edge of the holes fixed by the zero displacement boundary condition, then you can have a zero frequency gap. But that zero frequency gap includes the zero frequency, because such a plate cannot move, okay? So it's not too useful, let's say, in terms of application. So let's start. Let's say we take a solid plate, okay? And the excitations in a solid plate in the low frequencies is well known. That's a Lamb's wave in the low frequencies, and they can be distinguished into two types. One is the asymmetric mode, that's the best known, that's the bending wave, okay? The one on the left, that's called the A mode. That's the A mode, asymmetric mode. And there is the symmetric mode, so-called S mode. But for the very, very thin plate, the S mode is difficult to be excited. So usually, for the very thin plate, we only concentrate on the bending modes. So the bending modes follow equation motion that's fourth order in space derivatives. So it has a quadratic dispersion relation, whereas the S mode has a linear dispersion relation. And in fact, this is the continuation because of the Floquet block boundary condition. So this is a simple visualization of what these modes looks like. And of course, the bending mode is much softer, so the frequencies are much lower. So when we talk about the low frequency mode, is the bending mode that dominates. Okay, so the basic idea, the starting point of what I called zero frequency gap by using the mosaic plate idea. The name mosaic comes from, the ancient Greece, Roman mosaic, art. You have many of them. Maybe even in the Egyptian era, there are mosaic arts. So you divide a solid plate, okay, into many small finite sized plate, yeah? And we call them tile pieces. Each small plate is called a tile. And then each single tile will have discrete eigenfrequencies for their vibrational modes. That's well known, okay? Because every finite-sized system, the eigenfrequency or mechanical vibrational eigenfrequency will be discrete. So there will be zero frequency modes, and they represent the rigid body motion overall of the finite-sized plate. But starting at some lower finite frequency, there is a vibrational mode, and that mode is the what I would call locally resonant mode of the mosaic plate. But in order to have a zero frequency gap, we cannot apply that to a finite frequency, a finite plate. A finite plate just is a finite size effect. In order to have a zero frequency gap material, you must have an infinite plate. So we must stick those finite plates together to form what I would call a mosaic plate. Okay, the tiles put together for a mosaic plate that can have a zero frequency gap while retaining the overall rigid body motion, so it can move around. So that's the challenge, okay? And what we propose is the following. You have the finite size tiles, and you fix the corners of the four corners of the finite size tile. And if you just have a finite size piece, you fix its four corners, okay? Then you can say that piece is fixed, okay? It cannot move, right? Now, just imagine we don't fix that. We fix that relative to all its neighbors. That will essentially eliminate the relative motion of that piece with all its neighbors, okay? So it happens that such a connection will have retained the overall rigidity, static rigidity of the overall plate. You can imagine, right? So you can move the whole system around, but it will suppress the global bending wave at the low frequencies. So this is the realization, essentially. I'm telling you, and I will show you the results. So it is possible to have a zero frequency gap material. So in this theoretical model, and also experimentally tested and realized, we essentially used aluminum alloy, which is fairly light. You have the mosaic plate is 3 centimeter by 3 centimeter by 3 millimeter thick. And they are connected at each of the four corners by a central screw. So that screw is like 4 millimeters in diameter. And the screw will connect the four pieces together at the corner where they meet. And therefore, the most difficult part of constructing such a plate is to be sure the screws thread on the four pieces, they match, okay? So you have to thread the four pieces before it is cut. So you have to number them, okay? So once you cut that and you put in the central screw, what we discovered that just that screw is not sufficient. Why is that? Because a screw can have a second order lateral motion, and that's unstable, okay? So you want to eliminate such instability. So we use a smaller aluminum plate, 1.5 centimeters by 1.5 centimeters by 2 centimeters, 2 millimeters thick. And then there is a soft silicon rubber, okay, layer, and sandwiched top and bottom, symmetric. And there we add 4 side screws. They are smaller, like 3 millimeters in diameter. And in this way, when we screw them together, the soft layer will prevent the collective tilting to destabilize the system so that it can retain the rigidity. The whole system feels very statically rigid. So here is a more detailed picture of what we call the corner joiner piece. You can have essentially top aluminum piece, aluminum piece, silicon rubber piece, and the bottom silicon rubber piece and the aluminum piece, and they are all together. And you sandwich the mosaic plate in the center. And the soft silicon layer, besides having the function of preventing the screws from tilting, it also has a function of preventing the torque and the force being transmitted from the mosaic plate through the smaller top or bottom aluminum plate to its neighbors because we want to cut off the propagation of the bending waves. So the soft layer also functions in that case. It also plays a very important role in shielding the sound, which is normally incident on the plate. Okay, because it has a very small Young's modulus. So any normal displacement will convert through the silicon layer through the lateral displacement, bulge out on the side. So it's very effective. So they have the three functionalities, as I said. So we did a full waveform simulation on the whole system, very large scale. And each mosaic piece is separated from all its neighbors by 100 microns, okay? So you need fairly small mesh size. So the overall simulation is fairly large. And you can see a photo picture of the whole sample. And you have the schematic diagram. And on the right is the full simulation results. And there is clearly a zero frequency gap, very clear. But zero by itself is mode, is not lost. You can move that around, okay? And you can see that at 2.8 kilohertz, there is a mode which is a soft mode vibration. But that has a very, very small footprint. So it will not prevent the insulation of sound. For insulation of sound, the gap extends to 6.78, 6.8 kilohertz. So you have a fairly big window. And by the way, this upper frequency can be lifted further up by decreasing the tile size. You make that each tile smaller because here is 3 centimeters on the side. If you decrease that to 1 centimeter on the side, it will be increased to be much higher frequencies. But we want to compromise because we don't want to make the fabrication so difficult, because everything is done by hand. Okay, so you have many, many tiles to compose. So the overall sample is like 0.7 meters by 0.7 meters in order to have a valid test. So you can see that. And then we go to the experimental verification. So the first thing is that you do a point excitation. Yeah. So you have a point excitation, and then you use the laser vibrometer to detect the response. So there's a central line of the sample. And how do you theoretically explain this? Well, even if there is no homogenization theory, green function always applies, okay? When you have a point excitation, you want to measure a response in any physical system, that's perfect for green function, okay? We all know. So the green function in this case is given by the displacement divided by the pressure. And green function can always be expanded in terms of eigenfunctions. And in this case, the eigenfunctions are discrete, okay, even though we have an infinite plate. So we have a zero frequency mode. We have a soft layer vibrational mode, and we have a locally resonant mode of each tile. So we only have 3 modes So the green function can be expanded in the low frequency range in terms of 3 terms, very simple. And because the measurement point never coincides with the soft layer location, so the central term can be eliminated as far as we want to examine its in effect experimentally. And we have a term here that's due to the 2D wave spreading. And there's a term here due to the dissipation introduced by the soft layer, which is proportional to frequency, of course. And so this is the experimental result, you can see. And in all the cases, we always compare this with a reference plate, uniform reference plate with similar thickness and so on. And you can see on the top, that's for a uniform plate. Okay, so you can see a lot of oscillations. That is due to the discreteness of the vibrational modes in this 0.7 by 0.7 meter uniform plate. There are many vibration modes. So you have many oscillations, indicates the excitation of such modes. Now the blue is the experimental results for the mosaic plate, and you can see the horizontal axis are dBs, so they are logarithmic. So it's very much attenuated, as you can see. And the red line is the theoretical fit. We have using a least square fit by using the green function form, and it fits fairly well. And you can see there is a slight bulge in the middle, and that is really due to the overlap of the 2 Lorentzians. Okay, one at 0, one at 6.8. So in effect, the frequency response of the mechanical system of this mosaic plate is very different from the uniform plate. We can see this very clearly. And also, we can plot this as a function of distance as well as frequency, and you can see that at the bottom. And also, it agrees reasonably well with the green function predictions using the same parameter we already obtained. Then we go through the sound transmission. This is obtained by using the facility at Lamont, and they have a very first-class testing result for acoustics. So the sound source is in a reverberation room in which the source are 2 speakers placed at a corner, and they have an array of microphones placed at the center of the room. And these randomly scattered sound are captured by this array of microphones. And the sample is placed in a window separating this reverberation room from a semi-anechoic room, which is the receiving room. And so sample is clamped in a window. You can see this on the right. It's clamped. And on the receiving side, the signal is scanned by using a probe, a handheld probe. And the signal on the incident side is taken to be that received by the array of microphones. So so this is the measurement results, both simulation as well as the experimental results. And I must remind you, for the simulation results, for both something called the mass density law and for the sample, they are using normally incident acoustic waves, whereas experimentally, the incident waves are randomly scattered. So it's diffuse. Okay, so the incident conditions are very different. So you can see the dashed line is what's called the mass density law. It's basically Newton's law. Okay, if you have something incident on this, okay, at low frequencies, it moves in sync. It's Newton's law, and the uniform plate experimental results indicated by the yellow line agrees with that reasonably well, but then deviates at a higher frequency from the mass density law, basically probably because of its diffuse incident condition. Now, for the simulation, which is indicated by the blue circles, it has a very much higher transmission loss, and it goes down, has a similar trend, but much higher than the mass density law, but then flattens out at the lower frequencies. And the experimental result is represented by the red line, and the red line at the low frequencies is averaged, okay, over 30 hertz, because the lower frequencies, the signals oscillate a lot because the wavelengths are long and the reverberation room is not big enough to erase the discreteness of the eigenmodes in the room. So they have a lot of oscillations, but if you average, it becomes flat, very similar to the simulation. And at 50 hertz, it displays something like 13 dB advantage over the mass density law. But at 6.8 kilohertz, and unfortunately the measurement did not go that high, there's a sharp drop in the attenuation loss because the local resonant mode becomes effective. And if somebody can use this, it may become a sonic weapon. I'm joking, okay? Because it becomes a coherent source or something at the high frequencies. So it reproduces all the results. So now I come to the conclusion. So essentially, we have designed and realized a structure plate that displays a zero frequency gap for the fractal modes. The mosaic plate shows advantage 13 dB over the reference plate at 50 hertz. Both plates have similar mass densities. At the low frequencies, the mosaic plate displays qualitative different behavior from the mass density law over a broad frequency range. And the manuscript is going to appear in Advanced Functional Materials. But before I close, I want to pay my tribute to Eleftherios, not only for the purity of his dedication to science, but also for the humility and the willingness to act as a step upon which the younger generations can step up and gain a broader and higher view of science and the world. So with this, I congratulate you, surrounded by your legacies and admirers on your 85th birthday. Thank you.
Thank you.
Any questions?
Professor Seng? Okay, there were two buttons, I missed it. So we can take a couple of questions if there are any. Maria.
I miss you probably. Thank you for the very interesting talk. So it's a great, huge band gap is amazing. I would like to ask something that you probably told and I missed it. So these flat bands, why they are so flat, and where they come from?
The flat bands in solid state physics essentially indicates localized modes, right? Because a localized mode, if you can imagine a delta function, all the k's are the same. So it's totally flat. So it's essentially indicates a localized mode. Yeah.
This mode in this case is particularly located in what's the profile? Do you know? I mean,
yes.
This is the local resonance of some
local
particular
resonance,
material.
It's the first local resonance of the tile plate, the smaller plate, each tile. Okay. So if you make the tile smaller, then this frequency will become higher.
Okay, thank you.
Yeah.
Is there another question? If not, let's thank Professor Ping Sheng. Thank you very much, sir. The next presentation comes from Karlsruhe. It's Professor. So I guess there is something he cannot find the solution. He just said he cannot. He wasn't able to. So I would like to ask now Professor Wegener from Karlsruhe Institute of Technology to talk to us about metamaterials across different areas of physics.
Good morning, and thank you very much for the invitation. It's my pleasure to speak to you on this occasion, but it's also my honor, really, to speak on this occasion. I was first here at Forth and met Professor Οικονόμου about 20 years ago. Kostas Zoukoulis brought me here, and I was actually kind of anxious to share some of my research ideas with Professor Οικονόμου because he was already a hero at that time for me, and there are not so many heroes that I have. But I think he liked the idea. Actually, I'm not totally sure anymore. And today I would like to tell you a bit where this went over the years, the kind of things we have been doing. So I'm going to be speaking about metamaterials again, like Ping Sheng, but I'm going to share with you results from different areas of physics. You heard this started perhaps in elasticity, acoustics, then went to electromagnetism. But today, these ideas of artificial ideas are basically all around in solid state physics, and I'm trying to give you a flavor for these kind of things. So let me start with a definition. If you ask different people, you will probably hear different things, what a metamaterial is. This is what I have been using for many years. I understand metamaterials as rationally designed composites. So they are composites, but not something you just find somewhere. You rather design it by human intelligence and lately by artificial intelligence. And the point of these composites is that they would allow for properties that go beyond, in some sense, and that's the meta, the beyond, that go beyond the properties of the ingredients you have put into the composite. That's the whole point. So in other words, you get out more than you put in, and that is what I enjoy. To make this perhaps a bit more visual, let me say the same thing with this view graph here. Ordinary solids, like they are described in the very nice book by Professor Οικονόμου that you can find out there, The Physics of Solids, are made of atoms. This is not a secret. And you can arrange these atoms in crystalline and periodic form, or you can arrange them in random form, in glassy form. But at the end, typically what we do in solid state physics, we try to get away from all this atomic quantum mechanical complexity and try to describe the properties by this shaded region here. We try to describe them by continua, by effective media. Parameters such as a refractive index or parameters as a conductivity or as a Young's modulus. And the reason, again, is to hide all that quantum mechanical complexity. If you were to calculate the refractive index of, say, silicon from first principles, that's actually very, very hard. But it's very easy to work with this concept of a refractive index once you have accepted that. Now, the next thing we do is we take such ordinary solids and we make our own unit cells. We make our own atoms, if you like, meta-atoms out of it. And we do this by designing the function into these artificially shaped unit cells. And then we arrange these unit cells again in the form of three-dimensional crystals. That's what we like. You could also do it in a randomized form. And then at the end, we again map the behavior of this structure onto effective material parameters, such that perhaps at the end of the day, a user who would be using these materials doesn't even know what is inside, whether it's atoms inside or whether it's these artificial unit cells inside of these structures. A very interesting and still ongoing discussion is what are the bounds, what are the limits for such metamaterial properties? And let me illustrate that with words a little bit. Suppose you make a composite out of two materials, out of material A and out of material B. And suppose the property of material A in some unit is 1, and the property of material B in some unit is 10. So naively, years ago, I would have thought if you make a composite, you get something in between 1 and 10, which wouldn't be that exciting. But in many instances, you can get things that are outside of this interval 1 and 10. You can perhaps get 20 or 100, 1,000, infinite, plus infinite. Or in some cases, again, the interval defined by the ingredient materials is 1 and 10. You can perhaps get something negative, which has excited people quite a bit. You put positive effective behavior in, but you get something negative in a certain sense out. And sometimes you can get anything from minus infinity to plus infinity, which I find particularly exciting. But that's not the case for all properties and all structures. This is still being investigated by theorists, what the conceptual bounds are. And we have enjoyed over many years trying to explore these limits, see what is possible and what is not possible. And I will give you a couple of examples where we realize things that people said, including statements in textbooks. It's impossible, and I enjoyed that particularly. I will not so much speak about the early days of metamaterials that for me were dominated by optics, by electromagnetism, where negative refractive indices were a big deal. This is still very exciting because waves for which the energy, say, goes in this direction, but the phase fronts go just in the opposite direction, are really something scientifically and intellectually very interesting in my view. But I will not speak about these old things. I will rather speak about two groups of examples. The first group is about negative material properties. And the second group is about non-local properties. And I talk until somebody stops me or my time is over. I have to look here. So let me start with the negative properties. I have two examples for you. One concerns the Hall coefficient and one concerns the static compressibility in elasticity. So speaking about transport, like the Hall coefficient, the first idea that might come to your mind, well, maybe can I change the sign of the conductivity, of the electric conductivity? But that is not possible because that would violate the laws of thermodynamics. But what you can do is you can reverse the sign of elements of the conductivity tensor. And that's what I will describe to you. Just as a reminder, the Hall effect is very well known and used in every mobile phone. You take some semiconductor or some metal and you send an electric current through that material. In addition, you apply a perpendicular magnetic field, and then due to the magnetic component of the Lorentz force, you measure a voltage in the perpendicular direction, and that is called the Hall voltage. And what I have asked many students in many examinations on solid state physics is, how can you find out whether it's the positive charges or the negative charges dominating the transport in such a material? And the supposedly correct answer is, well, you look at the sign of the Hall voltage, or the sign of the Hall resistance, or the sign of the Hall coefficient. If it's positive, it's the positive charges that dominate. If it's negative, it's the negative charges that dominate. Well, I'm not asking this question anymore, because in the meantime, we have made materials where, say, the positive charges dominate, yet the Hall coefficient is negative. You can flip it around by structure, by geometry. And that's what I would like to tell you in this example. This has a long history in mathematics and theory. Very wise people like Graham Milton thought about these issues, whether it's at least conceptually possible to turn around the sign of the Hall coefficient. Some arrived at the conclusion that it's not possible, but later the conclusion was it might be possible. Actually, the suggestions were very complicated, so we thought about this a long, long time and arrived at this structure, which is comparably simple. It's a structure composed of rings, as you can see. It is a simple cubic three-dimensional lattice of rings, of tori, if you like, and they can be interlinked, like what is shown in this picture, or they could also be not interlinked. And that makes a big difference. So if you ask the question, why would this structure allow me to turn around the sign of the Hall coefficient? The answer is topology in real space in this picture. Now, this is not super simple to understand, but let me try. If you start from a disk of material, you can do a Hall measurement on that disk. And you can then also go ahead and punch a hole into that disk. That changes the topology of the material, that hole in the disk. And then you can go ahead and contact the inside of that disk with a hole in it. This is something that has been discussed under the name anti-Hall bar by people like Klaus von Klitzing, who got the Nobel Prize for the quantum Hall effect. And now what we do basically, and if you do that, it turns out by fairly basic electromagnetism that then you flip the sign of the Hall voltage that you would measure. Now, what we do is we basically now make a lattice, we make a crystal out of such anti-Hall bars, out of these rings, if you like. And if they're interlinked like that, that leads to a chain of the effective Hall coefficient. So what we are discussing here is a material like that. Graham Milton has called this a chainmail crystal because it looks like a three-dimensional version of a two-dimensional chainmail suit I might put on here. So then we started making such crystals, which is not awfully simple, but what we are doing for quite a while, that's actually what I talked to Professor Οικονόμου 20 years ago, is this technology of two-photon 3D laser printing, as we call it today. So we take a very tightly focused femtosecond laser, and then the laser in this white region that you see here induces a chemical reaction that typically solidifies the material. It brings it from a liquid to a solid state. And then we scan and do whatever we like by computer control. And at the end, we wash out the still liquid material and the process is done. Well, there are some subtleties to that, but I will not dive into this. You have an expert here at Forth, also Maria Kafesaki, who is in the audience, has been doing this for quite a while too. If you care about this technology, you may want to read about it in this review article, because I'm not going to be speaking much about manufacturing today in my talk. But along these lines, we have made these little test samples. I hope you recognize the rings, which can be interlocked or can be not interlocked. And then we went ahead and coated by conformal coating with atomic layer deposition, the structure with a semiconductor, zinc oxide in this case. And by evaporation, we made contacts onto this structure to actually measure in the usual way the Hall voltage and the Hall coefficient. You see one of these samples here in the optical microscope. We put some electrodes to make contacts, nothing special, but it looks just very nice. That's what I'm showing. And then we do normal Hall effect measurements. And here you see some raw data. It's not really important that you look at the details, but what you should see is that depending on whether these rings are interlocked or whether they are not interlocked, like shown by the blue and red insets, we get a different sign of the Hall voltage. Here the sign is different than here, and this means we have flipped the Hall coefficient. So at the end, a material that in this case had negative charges that lead to conduction shows a positive Hall coefficient. And we measured this as a function of the geometry. You basically see the retrieved Hall resistance or Hall coefficient as a function of some geometrical parameter. It's not important. And we can make an N-type material look as if it was a P-type semiconductor just by geometrical structuring. And that many people liked that. It made it onto the cover of quite a few journals, but it also created some allergies or criticism, perhaps, which is why I want to show you some more results. Some people misinterpreted this result in that we only flipped the sign of the Hall voltage. That would be trivial. I take two wires and I interchange the wires and I have the opposite sign. That's not the point here. The point is that we change the sign of some material coefficient, of the Hall coefficient. So we went ahead and made more of these devices. Here you see some technology examples. Again, we made it in a form that we can put these Hall bars onto integrated circuits. Here you see a little sample on an integrated circuit. And then we made little crystals, three-dimensional crystals, and it's the same crystal in the four images you see here, but in different orientations in three-dimensional space to look whether really the flip of the sign is independent of the orientation of the crystal with respect to the electrodes. And I will not show you the raw data for that. Trust me on that. It turns out that indeed it's an isotropic effect. The Hall coefficient, which is a scalar, is just changing its sign as one example. Let me switch gears and show you a totally different example from elasticity with a totally different mechanism, and that is on the static compressibility. Now, you read in textbooks that the static compressibility has to be positive, and you read different arguments for that. Well, you have to be careful with these arguments. First of all, just to be clear, I'm talking about a hydrostatic pressure that is exerted onto some body, some solid, some material. And then the hydrostatic pressure basically leads to forces that are pointing inwards of the material. And you would think it just has to reduce its volume as a result of all these forces pointing inwards. So in other words, the compressibility, which is basically the negative derivative of the volume with respect to that hydrostatic pressure that we have exerted, should be positive. And different arguments have been brought forward. Perhaps the most formal theoretical argument would be the real part of any response function in the zero frequency limit has to be non-zero, has to be non-negative. Like, for example, the permittivity epsilon cannot be negative really at zero frequency either. Other people have argued, a negative compressibility is like a negative Hooke spring constant, so that would violate energy conservation, and hence it's impossible. Other people have argued, that's going to be an unstable situation, so even if you can achieve it, it's not going to be stable. Well, it's all crap. You can do it with a metamaterial, and let me show you. So first of all, on the left is again a simple illustration of what positive compressibility means. You exert a hydrostatic pressure. Forces are inwards on all sides, so a cube would simply shrink, and that is what we call a positive compressibility. What I will show you is a metamaterial, a porous structure, that shows exactly the opposite behavior. You exert the same hydrostatic pressure, but it does not decrease its volume, it increases its volume. Now, before you think, that's trivial, this guy is cheating me, this is like a sponge and the air can go into the sponge and that's why you get a negative compressibility. That's not true. You take any ordinary sponge that is porous, you exert a hydrostatic pressure and it will also shrink. Actually, all ordinary porous materials also shrink. They have a positive compressibility. Yet I will show you a material that does expand. So where's the trick here? Well, where you have to be careful is with the notion of the volume here. What I'm going to call the volume is what I see as an experimentalist. I take this cube, I look at the faces of the cube, and they, so to speak, define a volume. And that, as I show you on the lower right-hand side, will increase. But careful, this is not the volume in a thermodynamic sense, and you should not insert this into thermodynamic equations, because there you should put the volume actually of the ingredients, say of the polymer material this structure is made of, or the air that is inside of this structure. That's if you want the trick here. But never mind, let me just show you what we did. First the design and then some experiments. This is one of the structures we have designed. It's again a three-dimensional structure that exhibits isotropic properties. It looks very simple. It's again a simple cubic lattice, and it's composed of these cubes that you can see here. And the cubes are connected by these funny little arms that you can see here. And I guess you wouldn't understand, I wouldn't understand why this should show a negative compressibility. So let me explain to you why it does. Let me first magnify one of the cubes, one unit cell of this three-dimensional crystal. And it again does not look very special. There's a cube and some little funny arms that connect all the neighboring cubes. So where's the secret? Let me cut open this cube for you on the computer. And it's hollow. That's the first thing. It's hollow and it contains air. That is actually important that it contains air. But it's not only hollow, it's sealed. The air that is inside must not go out. Otherwise, it wouldn't work in this case. So why does this show a negative compressibility? Well, let me exert a hydrostatic pressure on this thing, which will again lead to forces that are inwards on all 6 sides. And let me go back and forth a couple of times. If I increase the pressure, no surprise, these membranes are going to bend. They are going to warp inside because of the force that is exerted onto the wall. So this is without additional pressure. This is with additional pressure. So what's the deal? You must look at the little arms and what they are doing. And that's the smart part of it. The arms are connected to these membranes such that when the membrane bends or warps inwards, the arms go outward. And the arms connect the neighboring unit cell. So to speak, the unit cell is getting bigger because the arms go out. And this means the lattice constant increases. And this means the entire volume of this three-dimensional crystal is going to increase. That's the trick. Look at the arms. You will also see them in the experiment. And it's isotropic because it has cubic symmetry in this case. If you don't like to look at 3D images, that's basically the same thing in a cross-section. The arms go out. This increases the lattice constant or period of the structure, and hence it shows a negative compressibility. Again, we made such structures by 2-photon 3D laser nanoprinting. You see a small crystal that we made along these lines like here. It looks like what I showed you. You see these cubes. I cannot cut them open. They are hollow. Then they are damaged, basically. And if you care, by the way, you can ask me how we made this. This is quite tricky, actually. And they are, again, connected by these, you don't see this, by these arms here. And then we take the structure, so just to calibrate you, this is about a 50 micron side length here of the cubes. The thickness of the membrane, and that's a super important parameter, is about a micron thick. It's very important that it's sealed everywhere. It doesn't have any holes, this thing inside. And then if you look from the top, say, of this structure with an optical microscope, while we are exerting a pressure, you see this. This is real time and not magnified in any way. That's the real effect. If you really care, you must look at the pressure that is ramped up and down from 0 bar, I mean 0 with respect to the environment, normal ambient pressure, to 3 bars additional pressure. 3 bars is not so much. That's what I can blow into an air balloon just to calibrate you. It's not a very large pressure here. And you see when the pressure is large, the material is large, and when the pressure is low, the material is small, and that exactly corresponds to a negative static compressibility. If you look carefully, you will see at many points how these arms move. That's the mechanism that we built into this thing, that they go out if the pressure increases. If you look very carefully, you will also find that some of the cubes are defect. They have a hole in them. For example, this guy doesn't do anything, but that's not so important if the defects are not so large in number. This guy works, and all of the other guys here work very, very nicely. And there are other possibilities too. This is just one example I wanted to share with you. So let me come to a second group of examples that is different again, and follows a different spirit. If I was emphasizing so much this rational design of metamaterials, and this raises the question, so what principles can you use for design? And you heard in Professor Ping Sheng's talk already, you can use resonances to do funny things. You can use Bragg reflection to achieve certain goals like stop bands. You can use topology. This has been explored a lot. What I'm going to do in the next couple of examples, I'm going to use non-locality as a design principle to design very unusual behaviors. Now, to be clear, non-locality is a very well-known concept in solid-state physics. The Coulomb interaction is non-local. It decays over very many unit cells. But we are going to do this in a different sense. We will have much more control over the non-locality. The key point from what I show you now is that we will have some interaction with nearest neighbors in a crystal, but then we can say, I want some additional interaction, not with the second nearest neighbor, but perhaps only with the third nearest neighbor, and then not with the fourth. And then again, I want some interaction with the fifth nearest neighbor, just for example. So we have unbelievable control over non-locality, and this allows us to achieve actually quite many different properties. We looked at this in elasticity, acoustics, electromagnetism, transport, and diffusion lately. I will not show you all of that. I will show you two examples here that I hope you will enjoy. And the first one I picked is, I think, particularly simple to understand. It's Ohm's law. The fact that current and voltage are proportional to one another. And I have put this here in this form, that the current density of some solid at position X, I make this one-dimensional to be simple, is proportional to the electric field at the same position X. And the proportionality factor, I don't have to tell you, is the conductivity sigma in this case. And you can recast this in many different forms, whatever you like. I don't care. The main thing is current and voltage are proportional to one another. And as a result, I'm not telling you anything new. If you take a wire, a copper wire, for example, and you ask how does the resistance of this copper wire depend on the length of the copper wire, it's just proportional to the length, right? You double the length of the copper wire, you get twice the resistance. Well, this is not a result of Ohm's law per se. This is actually a result of locality. And that's what I will show you explicitly. So in non-local, in more general form, it means that the current density at position X will depend on the electric field or force at many other positions, X prime. And how far away X prime can be from X on the left-hand side is determined by this integral kernel here, the conductivity integral kernel that depends on the difference. So for example, if this was a simple Gaussian, the width of the Gaussian determines how far X prime can be away from X and still be relevant. And I want to show you that a result of such non-locality, a simple thing like a resistance of a wire is no longer proportional to the length of the wire, but it can actually have any crazy dependence that you want, which may be useful for sensing at some point. That's basically the thing. And in this case, I want to go through with you in some mathematical detail through the design process. I'm going to ask the question, can I actually design any non-locality that I want by a metamaterial. And I think you can follow this almost step by step. What I'm going to do is I'm going to use a Fourier transformation of this non-local form. I'm going to do a Taylor expansion. I'm going to Fourier back transform, and I'm going to put this in discrete form. Well, I'm going to do it slowly for you. The result is, actually the calculation is very simple. I find the result surprising. So I start here with this non-local form. Current depends on the electric field in a non-local form. If you do a Fourier transformation, you all know that this convolution integral becomes a product in momentum space. So the current at spatial frequency or momentum k will be proportional to the conductivity as a function of momentum or spatial frequency times the electric field. Next thing I do, if this is possible mathematically, of course, I do a Taylor expansion. There are constraints on the coefficients. For example, in one dimension, if you have a reciprocal medium, the odd terms have to be 0, but that's not terribly important here. And then I remember, if I Fourier transform this back, multiplying with k means in the real space domain basically a derivative. So I'm doing this for you here on this view graph. So this is the back transformation to the real space domain. And if you take these things together, I have reformulated this expression, which I started with, to this expression. Well, to me, this was actually surprising because if you look at this expression here, the current at position x depends only on quantities at position x and not on any other position. So where has non-locality disappeared? After all, I've told you these two expressions are mathematically equivalent. Well, it's kind of encoded in the higher order derivatives, because these higher order derivatives, so to speak, feel the environment, and the higher the derivative, the more it feels the neighborhood. And mathematically, these two things are equivalent. But now I can go ahead. Again, the task was I want to tailor any non-local behavior that I want. I map it on this equation, and now I approximate all the derivatives by a discrete form, basically by finite differences. That's what I'm going to do. I'm considering a lattice, and now I'm moving it again back to metamaterials with a certain period, A or delta x. I've written it down here for you, and you express all the derivatives approximately as differences between different unit cells here. And you do the same thing. I have not written this down on this view graph for all the derivatives. It's getting increasingly messy if you do it on a piece of paper, but never mind. Even I can do this. And what you get, and here I'm truncating at second order, is this set of equations that connects the current and the electrostatic potential. You don't have to look at this because I've put it for you in some hopefully easy to digest form, some symbolic form to start with. So here I have a one-dimensional arrangement. The blobs here are just connections between wires or resistors. The blue lines symbolize a certain resistor that connects these 2 points, R1 in my nomenclature. So these are kind of the nearest neighbor interactions. But now I also have second nearest neighbor interactions with the resistance R2. Here you go from this to the second nearest neighbor. And if you consider now more general forms where you account for any non-locality, that is any order derivative, you will additionally have third order interactions, fourth order, fifth order, etc. It's going to look very messy, but at the end, it's a simple resistor network I'm talking about. So here I've put it into more usual forms with resistors, as we would show this to students typically. If you leave away these red resistors, you would come up with a simple one-dimensional model for an ordinary conducting material, for a local conductor. If I go back, if you do the opposite, if you leave away the blue resistors in this picture, which I'm going to do for you here, it's actually kind of funny. Then you get in this case two, disconnected resistor networks. They are totally disconnected if you look at them for a moment. And if you express this in a bit more fancy terms, this is a delocalized zero mode of the system. You can take these two parts and shift them with respect to each other without invoking any energy. It doesn't cost you any energy. That's what people mean by zero mode. And it would do this everywhere, which is why I call it delocalized. So this is the extreme limit of a non-local behavior, that you get these zero modes. And I will tell you a bit about that. But this was just a conceptual resistor network model I've shown to you. Can you turn this into something that looks more like a metamaterial? And yes, we can. So in everyday life, you will find some simple cylindrical copper wires, but very often the wires we use in everyday life are made of many wires that are wrapped like what I show you here. And actually then you have a certain period already. You can call this a metamaterial if you like. I don't care. It doesn't have any special properties. You still have a normal ohmic local behavior. But now we modify this in the following way. And this corresponds to what I just showed you. We take two thick copper wires and we twist them like shown here. So far, nothing special. And then we take a thin copper wire in addition, and we connect it electrically at this green point. We wrap it around and then connect it again to the thick wires at this point. So all these wires are coated, so whenever they touch, there is no electrical connection directly. And we're going to do this in a way that the resistance of the thick wires from here to here is about 100 times smaller than the resistance of the thin wire. And if you had asked me 2 years ago, I would have said, well, if this resistance of the thin wire is 100 times smaller, forget it. You will get the same behavior as if you have no thin wire there. Well, I'm not saying this anymore because actually this is absolutely not true. You get a totally different behavior, and you can expand this. You can do it for third order interactions. Here you see the cross section just of these things here. So here you wrap 3 wires with this period, and you can create any long-range interaction, any beyond nearest neighbor interaction that you want. In this case, we have actually not used laser printing for once, but Julio Iglesias, who made these samples, has done it literally by hand from copper wires to show the principle. And you can see his samples here. And what you perhaps do not see, that's why I pointed out to you, this is the wire, the whole thing. So he made like 1 meter long samples. They look like an ordinary wire. And you can also bend them and do whatever you like. If you zoom into one unit cell, it looks like what I have described to you. There is some disorder, some imperfection, but that's totally unimportant. And you can take 2 thick wires, 3 thick wires, or 4 thick wires, and depending, this would be a second order non-local interaction, third order, fourth order non-local interaction. So I promised you in the beginning that the behavior would be different in that now the resistance of this thing is no longer proportional to the length of the wire. So we're going to do experiments just like that. We're going to probe the resistance over different lengths, and I'm going to show to you what that leads to. And here are some examples. I'm plotting the resistance in milliohms. That's not important. And we have done 4-point measurements because otherwise this is all dominated by contact resistances. And we do this as a function of length. This is very short. This goes up to 50 or so, 53 in this case, unit cells along this wire. Again, I emphasized the normal behavior would be that the resistance is simply proportional to the length. But you see, this is not at all the case. We get oscillatory behavior of the resistance as a function of length. And that has to do with the eigenmodes of the system, which I will have to see whether I can tell you that. So you get a totally different behavior. And in principle, I would argue you can get any behavior. You can map this onto effective medium behavior. Maybe that is not so important. And perhaps I also skip over this because I would like to spend a moment. How long do you think I still have? I'm going to try to wrap this up. So I'm going to show you basically the same thing now with Hooke's law. But I first want to make the connection to waves. This was totally disconnected conceptually, I think, from waves, but it is connected to waves, actually. And that's what I would like to illustrate. So probably in the book of Professor Οικονόμου, The Physics of Solids, you will find simple models like that we teach our students, that you have masses with a certain period. They are connected by simple Hooke springs, and then pretty much everybody in the audience can calculate the dispersion relation of these acoustic phonons, of these acoustic waves in this system. And some years ago, we asked ourselves, what do we gain if we add some non-nearest neighbor interactions, in this case to the third nearest neighbor here? So we would have springs between adjacent masses, but we also have springs to beyond nearest neighbors. That's what's shown here. This is easy to do on a piece of paper. You would get a dispersion relation like this, and the experts can see these are basically two Fourier components in a Fourier series, if you like. In any case, if you don't like to look at equations, this is how the dispersion relation of this thing would look like. For very weak non-local interactions, you would get the ordinary dispersion relation of acoustic phonons. I'm plotting frequency versus wave number to the edge of the Brillouin zone. This is the totally ordinary textbook thing here. But if you then increase the strength of the non-local interactions, you see a transition to a saddle point, to a minimum, to a very pronounced minimum in this case. And this excited us a lot because this resembles the dispersion relation of protons, if you ever heard about that, in superfluid helium, which was a big excitement many years ago. Lev Landau and Richard Feynman got famous for predicting this proton dispersion relation in superfluid helium, this dispersion where at first you have a constant velocity of sound, but then you have this funny stuff where you get a negative slope here as well, where you get a negative refractive index, you might say, where you get backward waves. But this is still a very simple model. So we went ahead and laser printed, again, structures, metamaterials, as we would call them. You see a beam of such a literally made material, which is a centimeter or so in height, contains micron features. This is actually measured by confocal microscopy, and you see the principle. We have these cubes here. These are the masses. They are connected by rods, and this is totally a normal one-dimensional chain. But then we have this awfully complicated looking construction that basically connects this mass to its third nearest neighbor. And the reason we do it in this complicated form is because we want to avoid in this case, local resonances that you might get from very long and slender beams that would move to low frequencies and disturb the behavior. We are kind of proud of making these nice samples. That's why I will bother you with some more images, in this case, electron micrographs of this weird metamaterial we have been making. And here you see some measured dispersion relation. That's the false color stuff. Again, I'm plotting frequency versus wave number, and you can see this S-shaped behavior like you would get it for superfluid helium and the sound in superfluid helium. The Roton, people call this the Roton minimum. This region is of particular interest to me because here you get backward waves without any absorption, actually, over quite some bandwidth. So how is that connected to static behavior? And I try to come to the end as quickly as I can. One thing I ignored for a while is that you can take this or any other dispersion relation and ask the question, are there more solutions than real frequencies and real wave numbers? And yes, there are. In particular, there are solutions where the wave number is complex, where it has a real part and an imaginary part. And I call them evanescent waves. Some people don't like that when I say that. Some call them ghost waves. I don't care. I call them evanescent waves. They have a real part and an imaginary part. And they are Bloch solutions. They are eigensolutions of the Bloch periodic problem. And strangely enough, there is also an eigensolution, a Bloch eigensolution at zero frequency. And I had not thought about it like that. And let me show you this here. This is an illustration of the band structure for the same model I have been discussing. I'm plotting frequency, but now not only as a function of the real part, but also as a function of the imaginary part of K. And you see, whenever you have some extremal point in the dispersion relation, here shown by the black curve, there are evanescent branches going away from this. So if you go to other parameters, this will look different. First of all, I emphasize that we care about this red solution because this goes to 0 frequency. It gives you a static eigenmode of the problem. And if you go back to this roton-like dispersion relation I talked about, in this case, this 0 frequency solution changes. Now it has gotten a smaller imaginary part of K, which means it will decay longer in real space. Or if we go to more extreme parameters, the imaginary part becomes yet smaller. So basically, such dispersion relations, I bet you find in any material for any property. So why do people normally not care about this? Because normally the imaginary part of these solutions is pretty large, which means they decay very quickly in real space. And in a finite size experiment, that means that you will get some modification of the behavior for the very last left and very last right atom, and nobody cares about that. I don't care about that. But as the imaginary part becomes small, these solutions go deep into the bulk, actually, and completely determine the behavior of the system. And that is what I would like to show you. I come to an end, don't worry. Just as the last logical step, these are Bloch eigensolutions. I'm going to be speaking, as any experimentalist, about experiments on finite size samples. So how do we make that transition? Well, we just take all the solutions we have for the periodic problem, and we put prefactors in front of this linear combination, and we put the prefactors such that they satisfy the boundary conditions of our problem. And the solutions we have are these static, we call them frozen evanescent Bloch modes. And you also, in this case, have a trivial, that's what an experimentalist says, trivial solution. You take a stick, you stretch it, you fix this end, you stretch this thing, then the displacement will just linearly increase from one end to the other. That's what you normally have for a rod or for some elastic spring or for some hook spring, if you like. Mathematically, that's actually an exceptional solution because it has the form of a polynomial type, an exponential Bloch function, but never mind, I will not get into this. So what should you expect on this basis? Well, you have seen this eigensolution. It has a finite real part of the wave number, and this means it oscillates in space. It's like a wave, but in the static case, it doesn't move, it's frozen, so to speak. And it will decay exponentially, but not decay so fast. And with this, I will come to an end here, definitely. So we, again, brought this into a form that we can 3D print this by 2-photon polymerization. And here you see the masses, you see the springs that connect the nearest neighbors. So far, so trivial, but now we can have connections by rods that, for example, bring you from this mass to its third nearest neighbor. And we have total control over how this interaction is. It's not just any long-range decay, it's a specific decay that we can arrange for. Never mind this. I show you just some measured images of such samples for a second-order connection, for a third-order connection, for a where am I? Second, third, and here it's a fourth-order connection, and these are the nearest neighbor connections. And we do very simple experiments. We take this rod that you see on the left-hand side made by laser printing, and we stretch it by components that we have also laser printed. We stretch it a little bit very gently by 1% strain, that there are no funny nonlinearities. And I think this is the last thing I want to show you. What you find is that then the displacement as a function of the position. So this is one end of the beam. This is the other end. And again, if you take any ordinary material, you fix it here, you stretch it, the displacement would just linearly increase from one end to the other end. But it's not like that because the underlying eigensolutions oscillate in space. So you get some superposition of these oscillating eigenmodes, and actually the measured displacement as the calculated displacement goes crazy and shows this behavior here. And this behavior depends totally on the boundary conditions, which I will not show you, maybe just in passing by. You don't want to see all these details. And as a result of this, again, the Hooke spring constant of this rod as a function of its length and that's the counterpart to what I showed you for the electrical case, has a funny behavior. If I plot the spring constant as a function of the number of unit cells, normally it should scale like 1 over the length. You double the length of a rod and its Hooke's spring constant should go down by a factor of 2. This is basically this textbook scaling, but you don't get that. You get these funny oscillations and a very anomalous behavior, even for very large specimen. With this, I am at the end. So I hope I have convinced you, if you were not convinced already, that metamaterials are actually kind of nice. It's like we are becoming artists. We design our own solids. It's solid state physics 2.0, if you like. In any case, these are composites. The effective properties of which go outside, go beyond the ingredients. So in a way, you get more out than you put in. You can put in very basic, very normal materials, polymers, gold, silica, you name it, and you get out totally unusual properties. If you enjoy this, maybe you want to have a look at these review articles we have published a while ago. And with this, should like to end. And once again, congratulate Professor Autonomy.
Thank you very much for this fascinating talk. We can take a couple of questions. Yes, Professor Christopoulos.
Martin, concerning really the non-local conductivity, let's say we take material with non-local conductivity in 1D, in which case the current will be a function of the derivatives of the electric field, right, as you indicated. Will the continuity equation impose further constraints?
Yeah, I mean, if you map this onto an effective medium description, you must be careful with the boundary conditions, because you must not only match the electric field, but all these derivatives, if they are important, which is sometimes not so easy in practice. That's why you have to be careful with these non-local descriptions when it comes to finite specimen. Yet they help me a lot in intuitively understanding the properties, because you can think about the properties in terms of Bloch eigenmodes of the periodic system, which I like coming from solid state physics.
But let's say I inject DC current in this system. Eventually, the electric field will oscillate. Is that correct? It's a function of position. Let's say I have your system and I inject DC current. Your electric field will oscillate?
No, the electric field will not oscillate, but what I jumped over, what will oscillate, is the electric current in space, which is kind of funny. So if you look at a part of this structure I showed you, and you apply plus, say, to the right-hand side and minus to the left-hand side, the overall current is flowing to the left. And there's a continuity equation, of course, for the total current. But locally, it can happen, as shown here, that the current is going in the wrong direction. What I show here in red is that, for example, the nearest neighbor connections, they oscillate in the direction of the current.
That's fascinating. Thanks.
Is there another question? Professor Fotis. Biological.
I'm not a physicist, but I'm a medical doctor. So I have a question on the definition of the metamaterial.
Yes.
Is the metamaterial the result of targeted work to develop a better product, or is it a random result of experimentation? What I want to say is that when you try to develop something, you get out more what you put in. But when you say you get out more than what you put in, you may get something which can be worse than what you expect.
Yes, so it's definitely not a random thing. That's what you were asking. It's rationally designed. That's my definition of metamaterials. I put this because you will also find lots of interesting composites in nature. If you look on the back, on the wings of butterflies, you look on the back of beetles, you look on plants, and you look carefully, you will find many, many very sophisticated and partly periodic, even nanostructures that have very interesting properties. For example, my bones, if you cut them open, you will find they're not a solid material, they are a composite too. And that composite has also very interesting properties. It can even have, to some extent, chiral properties, but I would not call these composites that you find in nature a metamaterial, at least not according to my definition. If you like, you call them metamaterial, but then you come soon to a point where you can call anything a metamaterial, and that's why I try to avoid this. So the way we use this, if we design it intellectually, often on the computer, sometimes on a piece of paper, and then we can realize it, that's what we call a metamaterial.
Okay, thank you.
Thank you very much. Amazing talk. I was very much interested. It's a bit of a technical question, but how do you make these closed, hollow structures with no hole, and then you have to empty the material somehow?
Yes. There's somebody who knows a bit about two-photon printing. It's actually kind of nice. So we print this shell, this cubic shell, but then the shell is solid, but the inside is still there. It's a liquid. So the way we do this is that we have designed special things at the edges that during the development process, there is a shrinkage of, no, actually a swelling of the material, I'm sorry, and that leads to very small cracks at designed points. And through these cracks, the liquid goes out during the development process. And now you would think, oh, now it's over, you have a crack. But then these polymers are basically like glue. Actually, glue is a polymer in a way. And then when it shrinks again, they self-seal, so they heal. And this is working amazingly well. I didn't believe it at first sight. The student found this kind of by accident, but you can engineer it such that it works almost all the time.
Okay, I think we can proceed. Thank you very much, Professor Wegener. And now we can move to the next presentation by Professor Sergei Bozevolny. I think this time I said it correctly, on multiverse of surface plasmons.
Thank you. Yes. Dear Professor Economou, dear audience, it's my great pleasure and even greater honor to participate in this memorable event on the occasion of the birthday of Professor Economou. And yeah, it's not for me to tell in Greece about this picture. Probably all know this Greek myths, and it's related to this phrase, standing on the shoulders of giants. And yeah, let's go to the introduction. And actually, it's related to the workshop that has been organized on emerging trends in optics in Odense, where we had very nice talks during 2 days with distinguished speakers and so on. I'm not going to discuss all the trends that emerged in the course of this workshop, but the concluding talk was given by me and had the title, Standing on the Shoulders of the Giants. So now I'll explain. That was kind of my recapturing the development that our group and me undergone over the years. And now I'll explain this title and make transition to the current presentation. So usually this phrase of standing on the shoulders of giants described to Isaac Newton, who said, expressed actually in the letter. If I have seen further, it is by standing on the shoulders of giants. Actually, it's just a very nicely formulated wisdom that has been around for years, but British apparently extremely proud of it. They even put this on the £2 coin. Whereas if you look on the history books or in modern days in Wikipedia, you'll see that it has been known well before Isaac Newton. And actually, the current understanding is that it came from William of Conches in 1123, where he wrote that the ancients had only the books which they themselves wrote. But we have all their books, and moreover, all those which have been written from the beginning until our time. Hence, we are like a dwarf perched on the shoulders of a giant. The former sees further than the giant, not because of his own stature, but because of the stature of his bearer. Similarly, we moderns see more than the ancients because of our writings. Modest as they are added to their great works. So you say if you would like to really use giants to be on their shoulders, you should read everything that has been you should read everything that has been written before you. Yes, and yeah, that is how I started my talk, and I related my professional development to many giants on whose shoulders I was trying to climb up. And this is the slide from actually my talk, Emerging Trends in Optics. You can see it here. That was devoted to the Professor Οικονόμου. With I told about the coming event. Of course, briefly about his biography, and the two most impressive for me contribution to the science, one in terms of the textbook, another in terms of the surface original paper that I have been really using in the course of my research. And even more than that, at the conference of surface plasma photonics in Japan, which was just like 1 month ago, you see, it's a surface plasma. It's essentially the same, right? So, of course, I also mentioned about this coming event. And indeed, about the impact on modern science, you can see from the Google Scholar that the top 2 places are for the book Green Functions in Quantum Physics, and the mostly cited original paper by Οικονόμου, that is this on surface plasma and thin films. Okay, so that is prehistory. So now we are coming to the subject of the talk, multiverse of surface plasma. So don't ask me what is multiverse. I don't really know. I try just to search for the visual impression. This is what I found look like multiverse to me on just Google. So as far as surface plasmas are concerned, for me, it started from this paper. It's really amazing. It's 69. And Professor Οικονόμου at that time was at around his PhD age. I believe it's related to his PhD thesis, maybe the main content of that. So, and from here, we are going around to different solutions, because this is what it's all about. It's about different surface plasma modes existing in multi-layer structures. Usual surface plasmons, long-range surface plasmons, short-range surface plasmons, and gap surface plasmons. There are many other modes considered in this very profound paper, but it's those 4 that are mostly being used in the latest development of plasmonics. And from these sub-universes, there were development to sensing by using surface plasmons, quantum emitters coupled to surface plasmons. This is the subject that I will talk a little bit at the very end of the paper, of the talk. Long-range based photonics, short-range based nanophotonics, and gap surface plasma-based optical metasurfaces along with quantum photonics. So it does look like a kind of multiverse created by this seed. And that's the approach I've taken in the further presentation. So surface plasmons, the first offspring. Well, we start again from this paper and look at the introduction just to appreciate the importance of this theoretical development is that previously the plasma oscillations, surface plasma oscillations, they were considered using electrostatic theory instead of complete set of Maxwell equations. And electrostatic means no waves that are propagated. So in this paper, the properties of surface plasma oscillations, they were considered by taking into account retardation effects and using complete sets of Maxwell equations. So this is by no means a simple feat, but this is what has been done, and that's why this paper is so famous. So surface plasmons, that's the solution of electromagnetic excitations where the electromagnetic waves in insulator, like our usual transverse waves, are coupled to longitudinal oscillations or waves of free electrons in metal. And when they're coupled, instead of the light line, we have dispersion corresponding to surface plasma. So from here, it's a very direct way to sensing. So I'm just showing my modern slides that I use in lectures to show surface plasma polaritons as the solution traveling along the interface, a distribution of the field. These are the two most important facts that I also actually picked up from the paper by Professor Ekonomou. That is, it's really hybrid waves. They are transverse and dielectric, so just like usual photons, but longitudinal metals, just like electron oscillations. And they are put together by boundary conditions. So if you start thinking about how to excite them, then this is the so-called total internal reflection, which is attenuated by exciting surface plasma polariton, and reflectivity goes to zero. And how goes to zero, at which angle or which wavelengths, it depends on the properties of the material, also the one which is at the top. And that has been used for sensing. So this is the modern sensors that are using this effect, tracking down the position of the minimum. And if there is something added on with anti-genes and capturing these molecules, then this minimum is moving. So there are different modifications of it, but this is really practical application. There is a company, Biocore, that are selling these instruments. So long-range surface plasma polaritons. Again, we go to the next chapter in the paper by Professor Ekonomou, and here it's about the three-layer medium where insulator on both sides of the thin metal film. And there are two branches. So this is branches long-range surface plasma polariton. So why is long range? Because you see it's so close to light line. That means that exponential tail of this wave extends very much in the insulator, very long. So it's delocalized. So most of the light is carried through the insulator, which is lossless, and therefore they can run for the very long time. You can view it as a hybridization of the individual surface plasma polaritons when you make the film thinner and make the symmetrical environment. This is how you get it. And this is what you can calculate losses. You see losses for plasmonic now are in the range of dBs per millimeter. So it's really long running, just a telecom, no matter whether it's gold or aluminum. And if you make a stripe, then it's very good for conducting light. It's not well confined, but it goes over the long distances. And the propagation loss is very small, and you can couple to thin moved fiber. So this is what we've been very excited launching photonics in 2001, our vision was something like that, fibers, and here the plasmonic hat made of long-range surface plasma polaritons with electrical constants and so on. So these are the brave individuals working on this project in the company that we founded, Micromanaged Photons. So we produced a lot of great papers. So notably, this paper, this is the first paper where the golden dream of anybody doing modulators in optics has been achieved. So the modulation of light in the form of surface plasma polariton was achieved by sending the current through the stripes that were guiding the light. So the stripes were guiding the current and the light. And that's why they were so efficient. Well, our company did not exist for long because the crash of the telecom market at the time. But I remember our advisor in the beginning of this adventure asked us, do you want to be rich or do you want to be famous? Well, obviously, my answer was, I would like to be both, right? Well, in the end, we did not become rich because the company ceased to exist. But as you can see from these citations, we did become famous, and there is one striking example becoming famous. So this transition from Sasha Baltaseva here to the famous Professor Alexander Baltaseva in Purdue, it's really, that was the start of her career in plasmonics and in science. Right, short-range surface plasma. So now we are back to the same picture, but looking at this branch, and this is short range. Why it's short range? Because you can see the dispersion is very far away from the light line. And that means the field of the mode is tightly confined to metal film. And that means that there is absorption simply because of the Ohm's law. But the size of the mode is very small. So when gold film goes to zero, the effective index goes up actually to the infinity, indicating better and better confinement for the short-range mode. Whereas, of course, the propagation length goes to, well, to close to zero. So it's trade-off between confinement and loss. So you see the propagation constant is inversely proportional to the thickness of metal. It doesn't depend on the wavelengths. Very, very interesting result. Anyway, but if you put this strip of metal, thin metal, on any substrate, if this is thin enough, short-range plasma polariton mode never leaks. It's guided by this stripe and confined to the substrate. And that allowed us to go to nanophotonics, where you can see what happens when you decrease the width of the stripe. It's becoming like nanowire, transmitting very nice and confined modes. And here's the near field images where the confinement down to 30 nanometers was demonstrated experimentally. But of course, the loss was increasing proportionally or inversely proportionally to the confinement. Anyway, we could transmit light along the metal wire, and that could have been used for the current, right, for the voltage. And this is what we did. It's a very simple modulator where the light was coupled through the grating into these coupled stripes. And these two stripes, they were used as electrons. Here it's applied voltage. And everything was on the top of lithium niobate, which is good electrooptic material. Of course, the electrooptic coefficient is small, very small, because the effect of electrooptic is small. And we could not make it very long. But because of the confinement, the effect was remarkable. You can see that this is our experimental structure with only 15 micron length. And you can easily see that applying, I think it was 30 volts to the electrodes, we could see appreciable switching between the output channel. So that is a relatively recent paper, but still 5 years ago. Still, after 5 years, that is the record that we established still holds the efficiency of 0.2 volts per centimeter and huge bandwidth allowed and very small energy consumption. So this is that is something as an individual component that's actually very practical. Insertion loss was around 5 dB, by the way. Okay, gap surface plasmons. Now we go to next chapter in the paper. And here we have inverse configuration, the metal and the gap of insulator, air or glass or whatever in between. And these are dispersions that can be calculated for different modes. Now, what is interesting to us is this branch, because it's again very far away from light line. So it means that the mode is very well confined. And this is called gap surface plasma because they propagate in the gap. So it's the field is pretty much constant across the gap. You can say it's like electrostatic capacitance mode, right? But it has retardation. It does propagate. And this is what happens when you decrease the gap. Again, mode effective index goes to infinity, indicating infinite confinement. At some point, the propagation length drops down, but not before slightly increase. It's maybe not very much seen, but it's first goes slightly up. This is a very interesting phenomena. I'm not going to discuss that, but the point is that the GSP modes with better confinement can actually exhibit smaller damping and longer propagation lengths, and therefore they're ideal for plasmon-based nanophotonics. There are other features that are very interesting. One of the features is that if you realize this gap plasmon waveguide, so it's not, so here you have a gap plasmon, but then it's limited in one direction and propagates perpendicular to the screen. Then the mode, gap plasmon mode that exists, shows the circular behavior of the electric field. And that means that the resonance we have here is electric field driven magnetic dipole, and therefore it's so narrow, and it can easily be calculated. And we also proven experimentally that you can realize it by extending substrates, extending gap layer of silica. The physics is still the same here. So it was breakthrough to show that it can be realized with continuous bottom metal and dielectric spacer layers. Well, the next part would be to try to use these resonances for influencing the reflected phase and amplitude. Going quickly because of the time limitation, here you can see that if the gap is small, then the GSP resonance is quite pronounced and the reflectivity is weak. So you can have complete absorption actually, and it has been used for complete absorption of light. But if the thickness is larger, then the absorption is not very large. The resonance is still there, but the reflectivity can be 90%. At the same time, the phase delay, the phase change when you move across the interface, it's close to 2 pi, even when the absorption is relatively small. And that was immediately interesting from the point of view of metasurfaces that were being underdeveloped from the ideas of Federico Capassa. And yes, after figuring out the physical mechanism of this phase change over 2 pi, we realized that by changing the width of the nanobricks, the length and the width, you can control independently the phases of two polarizations, two orthogonal polarizations. So that is a big thing that has been then exploited to make all different metasurfaces. Actually, this is Optics Express. It's probably one of the most cited paper in Optics Express. Usually, they're not that well cited. So we published review on this kind of metasurface where we showed all the amazing properties that can be done, like lensing in reflection, because it's a reflective metasurface, but two different polarizations, linear, they were focused at completely different places. It could be also at different planes, actually. Now it's in one plane, but it's completely independent. We showed the excitation of surface plasma electrons simultaneously with abnormal reflection. There is this achromatic behavior shown by Professor Jinping Tsai. There were many developments. We are not only alone moving this ahead. So, right. Now I'm coming to the last topic, because as I said, I don't want to really delay you, but because the break for lunch should have been already started. Anyway, so here is the point of going back to surface plasms, going back to basics. So I showed you that surface plasms can be used for sensing, and they are used. It's very practical. But here it's a use in quantum nanophotonics. What's the idea here? So imagine that you do this usual structure, like for any surface plasma experiment, substrate, and then the metal, gold or silver. Now, at the top, you make the metasurface array. I will tell briefly how it can be designed and fabricated. But you made it around quantum emitter. In this case, supposed to be nanodiamond with only one vacancy. Nitrogen or germanium or silicon or tin, whatever the valence you like or whatever the property you would like to explore. So what happens next? So you send the pump light that excites radiative transition. It's a radiative dipole transition here in this quantum emitter. But even though it's radiative, the trick is because it's so close to metal and so much interacting with surface plasma, that is really tightly confined, so it should be away from the light line. It should be more close to surface plasma resonance, that practically all, up to 85–90% of the energy goes into the surface plasma waves. So it's non-radiative transition in something that's spreading the light all over the surface, right? And then these surface plasma waves, they're scattered by metasurface up. So if you wish, this is some kind of meta-atom where we excite it here, but we have the light only from the metasurface. And that allows us, because it's a large area, to have well-collimated thin photon source. And by making different nanobricks, differently arranged, different patterns, we can influence any property of this radiation. This concept from 2020, so it's 5 years ago, and with this group of very talented individuals, we have been working on this concept for 5 years, and essentially there was nothing we could think, we could not do it, right? And it's all single photon sources. We produced single photon perfectly circular polarized sources, encoding also orbital angular momentum, where vortices with topological charge 1 or 2, and this is just Gaussian beam. We produced several beams moving in different directions. We produced thin photon radially polarized beams. We could send this well-defined beam to any directions we wanted. We could entangle two modes of different left and right circular polarizations that were encoded with different orbital angular momentum. So it's not entanglement between two photons. It's entanglement between two radiation channels. The photon is still one, but it can be in one mode or another mode. And the rule of entanglement and the way to characterize it is exactly like in the usual entanglement in quantum optics. And we showed that you can go to higher order, higher dimensional space by extending the number of degrees of freedom that are entangled up to 4 and potentially to 6 and so on. One could send the different polarizations to different directions. So, and of course also do linearly polarization, not only circular, but also linear polarized thin photon sources, all thin photon sources. So quantum emitter surface boson coupled metasurfaces, they really showed seemingly impossible multi-dimensional entangled polarization and angular result thin photon generation. Was it all? Well, we don't think so. So actually, the very next step, that has been reported, you see, it's online only 10 years ago, where we made it tunable. So here, with our usual device of metasurfaces around thin photon source or quantum emitter in general, we added MEMS. We put it on the MEMS mirror and another substrate which was moved by MEMS structure was wavelength-dependent multi-layer, you can say Bragg filter or whatever. So, but it was a filter with 2 transmission windows, one for the pump and another for the radiation out of the thin photon emitter. Because the pump is a short wavelength, relatively 532, but the emission is around 650. And then by moving, it's very good Fabry Perot cavity, by moving back and forth this multi-layer, we could tune the wavelengths of the emission that comes out of it. So everything is put quite nicely arranged with as a MEMS device with all the accessories and looks very friendly to use. And the radiation is well confined beam. It's not like spreading everywhere. And as far as tunability is concerned, here are the experimental results where the voltage was gradually changing and the emission that was coming from here was changing the spectrum. So essentially we did see the movement of the top of the emission by 1 angstrom. So it was well resolved, and because the spectrum from the NV vacancy, nitrogen vacancy was narrowed down to 3.7 nanometers, and this is what was moving. But it's not all. We use the possibility to produce with these 2 sectors to influence one linear polarization, and with other 2 sectors another linear polarization. Why? Because you should remember that surface boson polariton, they have in-plane component oriented radially. So when they travel radially in all directions, when they travel here, it's this component dominant. When they travel in this direction, it's perpendicular component dominant. So we use both of them, and we directed them at different wavelengths. So that the output for, let's say, vertical, even though I hate it, I mean vertical, where is vertical? It's all on the plate. But for the sake of simplicity, for vertical, the line of emission was here at this wavelength, and for horizontal polarization, it was here. And then just changing the voltage, we could switch from one to another, switching wavelengths and the polarization simultaneously. So now to this list of seemingly impossible, I have added dynamically controlled thin photon generation. Okay, so acknowledgements. Of course, that's the Center for Nano-Optics. This is where the people working with me are present. Not all of them, but most. And I also should acknowledge the participants of this 2 days workshop with my dear friends Vlad Shalayons, Sasha Baltashev, Boris Chichkov, that was the inspiration for the talk on shoulders, on, you know, standing on the shoulders of giants. That was just recently. And okay, instead of outlook, I should think of birthday present, shouldn't I? And you know, I can say lots of things, but I found that all the nice words that could have been told there, told either in this audience or actually a long time before, because we are dwarfs on the shoulders of giants. So just use the words from my favorite writer, that youth is the gift of nature, but age is a work of art. And at this point, I would have liked to show a picture of me and Professor Ekonomou at our previous meetings, but we never really were that close standing. Apart from one occasion, it was a 60-year birthday of Kostas Sakoulis. And here we can see Professor Ekonomou and another hero of my youth, Professor Vysela. He was my professor at Moscow University, and me standing here, quite humble, and I'm still humble, of course, when thinking about these giants. Dear Professor Ekonomou, a very happy 85th birthday to you. Thank you.
Thank you very much for this excited talk. Do we have any questions? Are there any questions in the audience? I have a feeling that people are getting hungry.
Yeah, hungry.
So, you know, we are standing between. So if there are no questions, maybe you can discuss with Sergey later. Let's thank all the speakers of this morning. Now we break for lunch. It's served upstairs. Outside, okay. And we are going to meet again at 2 o'clock. I'm saying also for the people who are following us on Diavlos, okay, that will start again at 2 o'clock for the next session. So thank you very much.
So the next two talks by Professor Dimitris Christodoulidis and Professor Efthymios Kaxiras. Then we're going to have a nice music event, right? And maybe you have to decrease. Yeah. And then we're going to close the event with speech from Professor Ekonomou. So the next talk is a great honor and pleasure to have Professor Dimitris Christodoulidis from University of Southern California, who is going to talk about optical thermodynamics. Thank you very much for accepting our invitation. Yeah, the floor is yours. Yeah, and you have everything.
This wonderful event for the 85th milestone of Professor Ekonomou. Professor Ekonomou, as everybody indicated before me, is one of the most notable figures in physics, not only within the Greek environment and the European scenery, but internationally. I never had the opportunity or the luck to really work with Lefteris, but I always read with great interest his works. Occasionally we use them, especially the one pertaining to localization with off-diagonal disorder, the work that he did with Kostas Sakoulis in the past. But in any event, as Maria indicated, what I will be talking over there, what I will be sharing with you today is what we call optical thermodynamics. It is a topic, from what I understand, that Professor Ekonomou took over the years, tirelessly. And this is an area that we have been pursuing for the last 5-6 years. This work is done in collaboration with many talented people. Mercedes Hajavihan, who is going to be giving a talk tomorrow, I guess here at 4th. Frank Weiss from Cornell, Ulpeschel from Jena, Kostas over here, and Nikos Efremidis from the Department of Mathematics. In any event, let me proceed to the main topic of, say, this talk. So, before I do so, I would like to put everything in some perspective. We all aware, really, we are all very aware on which pillars our technology really relies on. Perhaps the first one is the transistor. The other one that actually really the communication era is the laser and the optical fiber. So fibers have been used not only for telecom, but also for several other applications, and in particular, say, in the nonlinear domain. So by exploiting the nonlinear properties, say, of guided wave systems like fibers, people can actually do these days nicely supercontinuum generation, pulse compression, parametric oscillators that are extremely useful, soliton compression, and so on and so forth. Nevertheless, if you by any chance try to really delve into this topic, very soon you're going to come across, say, with the Bible of nonlinear fiber optics, which by Agrawal, which if you carefully really look into it, you will understand very soon that this is only meant to be mostly for single mode fibers. Interestingly enough, the fiber, after it came from Corning in the early 70s, it morphed into mostly multi-mode structures, fibers that can actually support hundreds of modes. Nevertheless, by the early 80s, people understood that the complexity of the multi-mode structure was prohibitive, and as a result, eventually the entire technology went single mode. Single mode fibers are very, very simple to understand, and as a result, after the 80s, that completely dominated the landscape of optics. Nevertheless, what goes around comes around. So in the last 10 years or so, we have seen a renaissance in multi-mode optical systems. And the reason is very simple. If one mode can carry, for example, 100 gigabits per second, imagine what will be if you have a fiber with 100 modes. In other words, you scale the bandwidth by 100 times. And of course, bandwidth for us is always something extremely useful. What else actually enabled this, this revolution is the very fact that we have now technologies that allow us to preferentially excite modes and preferentially, say, interrogate modes. So we can excite particular set of modes and then also interrogate them at the same time. These technologies that evolved in the last 10 years were crucial, really, to see the multi-mode fiber systems back. Of course, for many of us that come from nonlinear optics, that was another opportunity to really see how multi-mode fibers really fare, right, in the presence of nonlinearity. So, and the reason is that we knew all along that that area was underexplored, and perhaps something was going on over there that could perhaps exploit or use, and so on and so forth. So by 2015, several activities went on. So we saw new classes of dispersive waveforms, parametric stabilities, multi-mode solitons. And then around 2017, this is a work between us and Cornell, the group of Frank Weiss for the first time was able really to achieve spatial-temporal mode locking, where the modes were not only locked in time, but also locked in space. And as a result, that leads to high power levels. They're extremely useful, right, when it comes to this particular class of systems. Nevertheless, I may say, in spite of all these activities, most of the effects we observed during that period were kind of complexifications of what already existed in the single mode domain. At some point, however, effects start to appear that had no counterpart whatsoever, right, in what we knew before. And one of them is what we call eventually the beam self-cleaning effect. So what is the beam self-cleaning effect? You take a fiber that supports, say, 300 modes. And then, of course, if you linearly excite it at very low power levels, what you see at the output is a highly speckled pattern like this, very dirty one, that results really from the interference of hundreds of modes. However, as you gradually increase the power, eventually up to 10 kilowatts, 40 kilowatts, and so on, this pattern here transforms to this one. It looks to the eye that is much cleaner, and as a result, we call it the beam self-cleaning effect. Interestingly enough, it was observed independently by 3 groups. So by our group at Creole, by the group of Frank Weiss at Cornell, group from France, all of them pointing out exactly the same effect. So it was there to begin with. And at the same time, it started puzzling everyone. Why? Because it wasn't really coming because of Raman, meaning it was occurring before even the first Stokes line came along. It wasn't self-focusing. Self-focusing levels would be megawatts, not 50 kilowatts. But at the end of the day, it was always there. We knew it was a nonlinear effect, but then again, why is this happening? That was something we didn't know at the time. And for a couple of years, it was puzzling everyone. Of course, anyone in optics, when confronted with problems of this sort, he will be quick really to use what we know, nonlinear Schrödinger equations, or these are nonlinear wave equations that we can actually simulate by brute force, and then perhaps from there we can tell what is going on. Of course, what I'm showing you over here is what it will take to really simulate 2 modes, right? But imagine, for example, I give you a system that has 1,000 modes. Then before you even run your simulations, you have to compute maybe 1,000 propagation constants, 1,000 cell-phase modulation coefficients, 1,000,000 cross-phase modulation coefficients, and then a trillion cross-phase, 4-wave mixing products. That you have to do before you start simulating. But the problem is not really so much simulating. The problem is, even if you simulate these evolution equations, what you get at the end, it looks like garbage. Unless you know how to sift through the data, at the end of the day, it makes no sense. You have to know what you are doing if you're going to interpret really the output of the simulations. So at some point, my group, we decided that it's about time we abandon what optics people do and resort to something entirely new. And by that, I mean, let's use statistical mechanics or optical thermodynamics to understand what is going on. So what I will be showing you over here, right, it's a new theory governing really nonlinear multi-mode systems by use of statistical mechanics or optical thermodynamics. It started with a paper in 2019. Many other, subsequent papers were published by Kostas, Parto, and so on. And pretty much it goes like this. So what justifies the use of statistical mechanics in such complex environments? Well, the dynamics in these systems are not integrable and therefore chaotic. If they're chaotic, they're inherently ergodic. So that's the first element that you need to have before you proceed any further. The other issue is what one needs to know before deploying this thermodynamic theory. Amazingly, very little. All you need to know is how many modes your system supports. If it's a fiber, all you have to tell me is this fiber supports 500 modes. If it's a cavity, tell me that this cavity supports 300 modes. In addition, you need the linear spectrum of the system. So if you're dealing with a fiber, you need the propagation constants. If you're dealing with a cavity, for example, you need the eigenfrequencies. And this is all you need. The next ingredient that is required is to identify the conserved quantities. In this case, say, of a fiber, and I'm mostly going to concern myself with fibers. Why? Because they're simple. The conserved quantities, of course, will be the total power. If you put in a fiber, say 50 kilowatts, definitely you're going to get 50 kilowatts after 2 meters. The other one is what is a silent one, is what we call the internal energy of the system, U. U is the sum of powers in mod I times the propagation constant. This is another conserved quantity. It's what we call the internal energy of the system. In reality, however, this has nothing to do with the energy. In what this represents, it's the electrodynamic momentum of the optical field as it goes down, say, the pipe. So essentially, one can show formally that U is proportional to the TZZ component. This is the Minkowski electrodynamic momentum. And as a result, it's conserved. So these two quantities, P and U, are conserved. In case, of course, your fiber is supercircular, you may have the optical angular momentum and so on and so on, but most of the times we don't. We only have these two. So how do we go about it? Well, the next thing you can do is the following. Let's say you inject something like 10 kilowatts in an optical fiber. You can actually break the power in small packets, let's say nanowatts. So if you break it in nanowatts, say if you have 1 kilowatt, say, that will correspond, say, to 10 to the 12 packets, or maybe 10 kilowatts, that would be 10 to the 13. And then you're asking yourself, in how many different ways I can distribute these indistinguishable packets in M distinguishable modes. Of course, it's an easy problem in combinatories. This is something we touch even in basic classes of statistical mechanics. This is what you get. So the number of packets is conserved, of course. There is also the conservation that comes along from the internal energy. And then once you have a counting of your microstates, then you have to use Boltzmann's law. S, the entropy, must be the logarithm of W. And as I said, you have no other option anyway. At the end of the day, it is written on the tomb of Boltzmann himself. So once you really extremize the entropy, as required by the second law, in the presence of two constraints, then before you know it, you find that the number of packets per mode is given by this Bose-Einstein distribution. The Bose-Einstein distribution, by the way, has nothing to do with H-bar. It's a statistical law. Occasionally, it's even used in the stock market. Here, the same thing applies. Nevertheless, there is something interesting going on in the systems we are discussing. If you remember, you have packets in the trillions. If you have only 100 modes, you understand the loading per mode will be a huge number, right? In essence, that would be in the billions. The only way this will be in the billions would be if the exponent is very small. And if the exponent is very small, then a first-order Taylor series expansion drops the entire thing over here in this simple expression, which is nothing more than your Rayleigh-Jeans distribution, as you will see. Notice that if, for example, I had to do this for the sunlight, the number of photons per mode, it would have been 10 to the minus 2. Here we're talking billions. So that's why we eventually end up to have a distribution that is given by a Rayleigh-Jeans. And if you want to rewrite it, the end result is this. The power in mode I, it's minus T. This is an optical temperature that has nothing to do with the temperature of this environment. It's the temperature of the optical gas over the mode eigenvalue epsilon I, maybe the propagation constant of that mode in the fiber, plus a chemical potential. On top of that, you can show formally that the entropy of this system, S, is the sum of LMPI. Very different than your familiar Gibbs-Shannon, say, expression. So armed with this, now we can proceed further. So the next thing you want to do is build in a healthy manner your entropy. This is extremely important. So S, the entropy, must be a function of other extensive variables. In this case, of course, it will involve U, the momentum or internal energy, the power P, And then it so happens you have to also include here the number of modes m. It looks very innocent, by the way, but it took us 6 months to understand that this m should be there. If m is not there, and this is where everybody else before us went wrong, your entropy is not extensive. And if your entropy is not extensive, which is an axiom, by the way, your theory is good for nothing. So essentially now, knowing that you have a healthy entropy, you can now go ahead and take it from there. So in this respect now, you can write down the fundamental thermodynamic equation where the derivatives, the partial derivatives of entropy with respect to U, P, and M give intensive variables like the temperature, the chemical potential, and something that time we call the optical pressure, even though, to be honest with you, we didn't know what that P hat was. So now, what is the optical temperature in these settings? Is that just something that is meant to really characterize a distribution? Does it mean anything? In reality, you can show that these temperature and chemical potentials are true thermodynamic forces. So essentially, if I have two subsystems in contact, like these two lattices, for example, one set at a higher temperature than the other one, right? You're going to see exchange of momentum. So momentum will flow from a hot subsystem to a cooler subsystem as expected by the second law. The same happens if the chemical potential is higher between two subsystems, in which case mu, the difference in chemical potentials, will drive a flow of power between the two. So they are not just some numbers. They are really true thermodynamic forces in this particular respect. So the next issue is there is, interestingly enough, a universal equation of state that describes these systems. Amazingly, it's very simple. It states that U minus mu P equals MT. To some extent, you may say this is analogous to what they teach us in high school. PV equals KBT. But once you have this universal equation of state, you can actually predict the entire evolution of your system. You can predict the end temperature of your system and the chemical potential, provided you know exactly the input conditions. In other words, if you give me the power that you injected and the way the power was allocated initially in the various modes, I can tell you where the system will equilibrate at thermal equilibrium. So once you find mu and the chemical potential and temperature, then you know everything about the system. And interestingly enough, there is a uniqueness and existence theorem associated with all this. In other words, even it's unique, that the solution always exists if you know the initial conditions, and that solution is unique. So one can formally actually prove this. Now, if by any chance you see a religious distribution, you should know right away that your system already has undergone thermalization. There are some sick cases, some funny cases where thermalization doesn't occur. If the system is integrable, or the system is very, say, if it's very, say, random, right? If it's an Anderson, heavily Anderson system, then thermalization fails. But on most occasions, it thermalizes. And what is very interesting also is that the nonlinearity itself doesn't matter. You can have chi2 nonlinearities. You can have chi3 nonlinearities. You can have even artificial nonlinearities. At the end of the day, everything settles and thermalizes to the predicted Rayleigh-Jeans distribution. Your nonlinearity is inconsequential. Essentially, I call them, it's like in the morning when you have a cup of coffee and then you drop some, some milk over there. If you use your spoon, yeah, of course, it will homogenize the entire system, reach maximum entropy. So the your nonlinearity is like your spoon. It doesn't matter if your spoon is silver or wood. You can even use your finger. At the end of the day, it will thermalize. So now, does it make sense? Or whatever, meaning does all this theoretical framework make any sense? So we have, of course, to see if we can actually verify all this experimentally. So the first time we saw the relative distribution, it was in experiments with Frank Wise in 2022. So essentially, you can see you excite the system arbitrarily, and then eventually ends up in this beautiful relative distribution. By the way, the dotted line is what you expect from theory. The rest is from the experiment. And then you will recognize that at 50 kilowatts, where the relative distribution comes along, you get this beam self-cleaning. So the beam self-cleaning that I mentioned before, it was nothing more than the system itself trying to achieve maximum entropy and thermalize. In a subsequent experiment that we done together with Mercedes and Ulf Peschel, we saw thermalization in lattices. These are nonlinear mesh lattices. These are fiber systems that actually artificially produce lattices. And then, interestingly, these systems, these are systems with 52 modes, you can relax in positive temperatures where the ground state is favored. Most of the energy eventually is distributed in the ground state. This is the initial profile of excitation in the modes. Or you can relax the system at negative temperatures, where as opposed to really have the fundamental mode to really be preferred, is the highest order mode. So both positive and negative temperatures are possible in this respect. In all cases, experimentally, we monitor the entropy, and of course, always increases as you expect by the second law. In this particular set of experiments, for the first time, under negative and positive temperatures, we did adiabatic expansions. So essentially, adiabatically, we expand the array, and then one can formally prove that U over T during adiabatic expansion is constant, or mu over T is constant. So if by any chance you compress a lattice, the lattice heats up. If you expand it, it cools down. And what is very interesting is that we can observe these processes at both positive and negative temperatures. Negative temperatures, by the way, were first predicted by Osanger in 1949. Nevertheless, there is no physical system we know of where you can actually see a typical thermodynamic process at negative temperatures. Negative temperatures are highly unstable because they touch the environment. Our systems are so isolated. You can do just about anything you want simply because they are not as stable. At the same time, we saw Joule expansion effects in these same arrangements are both positive and negative. And of course, once you have all these ingredients, people can start really dreaming about cooling machines, right? Machines where you can actually take a cold system and further cool it through adiabatic expansions and compressions by dumping excess, say, momentum, say, from the cooler to a hotter system, pretty much the way your refrigerator or your air conditioning system works. From the very beginning of this project, what we are interested in was to really cool down a beam. So if you see a beam like this is a beam at very high temperatures, very regular, almost good for nothing. However, if by any chance there was a way to really cool this beam without losing power and transform it into a beautiful Gaussian beam, the ground state, then you can do things. So the first thing we came across was a Joule-Thomson process. So those of you who remember the Joule-Thomson effect, what is the Joule-Thomson effect? It takes place whenever you are dealing with a non-ideal gas, a dense gas. If by any chance you allow a dense gas to expand rapidly through a throttle, then this gas will expand in such a way, will overcome really the intermolecular energy by expending its kinetic energy. And once it expends its kinetic energy, of course, the end temperature will be close to zero. In optics, there is something kind of analogous to that. However, it also occurs through these energy transformation processes, but it works somewhat differently. You see here I have an array, a multi-mode system, and I'm injecting light in one side. Linearly, if I do that, I'm going to be exciting pretty much every mode over here. However, if I excite only one side at a particular, particular power, all the energy goes into the nonlinear component of the Hamiltonian, which is like the intermolecular interactions I was telling you before. And upon expansion, right, this transforms into kinetic energy, the kinetic energy that corresponds only to the ground state. So irrespective what element I excite here in this 37-core array, it always drops into the ground state because of this optical Joule-Thomson process. And this is what we see here. We excite different sites, and then we decompose the modes at the output. And of course, at the end, you see that even though linearly this is the distribution of power among modes, eventually more than 80%, drops in a very, say, faithful manner in the fundamental mode. This result was published last January, and along very similar lines, we made possible the prospect of always, irrespective how we input light in, say, a multi-port system, always receiving it, say, from the center, from the zero port. Something that is impossible really linearly or otherwise, unless, of course, you involve gain. So thermalization, again, comes along in these discrete lattices, and irrespective how you do it, because you see what you get here is a Joule-Thomson effect, where light thermalizes at very low temperatures, and as a result occupies the fundamental mode. So essentially, however you come along, and these are experimental results, right? However, whatever input you excite always exits at the zero port because of this energy exchange process, because of thermalization. But the one I'm very excited about is what we call coherent beam combining. So what is coherent beam combining? Well, I don't know if you like Star Wars, right? Those of you who are familiar with this, they know about this, the Death Star. At some point, 8 beams really combine into a single beam so as to shoot at the target. It looks good, but it's very difficult. Essentially, to do that, even if you buy 10 identical lasers from a vendor, you cannot put them on the same mode. It's just prohibited. If the laser has a finite line width, the phases really flicker among lasers, and it's impossible really to do beam combining. So beam combining, of course, is important for these fellows over here, meaning the whole idea is to really get 200 kilowatts and shoot at the target. And typically the most expensive component in these directed energy weapons is how you really get, say, 37 solid-state lasers and phase lock them in such a way so as that they can combine in a fundamental mode. Most of the research goes on that, on the phase locking. So essentially the way it's done right now is just I look at, 37 lasers, 50 lasers, whatever, and I have a Maxwell demon that actually can tell where the phase is to rectify the whole thing. So coherent beam combining, as I said, relies on phase synchronization schemes, which are actually extremely complex, right? So essentially, can anyone do anything about it? Well, unfortunately, you have something called, brightness theorem. The brightness theorem prohibits really you from increasing the radiance of a source. It is direct byproduct of Liouville's theorem, right? So essentially, the brightness theorem tells you cannot do it. However, and by the way, interestingly, there is an analog of the brightness theorem in high energy physics. This is better known as the emittance theorem. Emittance, what is the emittance of a proton beam? Is the spot size times the angles, right? This is supposed to remain invariant because of Liouville's theorem. However, in high energy physics, people know that if the particles exert interactions among themselves, if there is no linearity, then the emittance can change. Why? Because even though the Liouville's theorem is always valid, the brightness theorem and emittance theorem being subcases, they are actually reductions on the Liouville's theorem, they have an Achilles heel. So what is the Achilles heel? Is nonlinearity. So can we use nonlinearity really to do something of this sort? In other words, can I use nonlinearity to produce from a mixed state a pure state? In quantum mechanics, it's impossible. Why? Because it's linear, it's a linear theory. A unitary transformation can never take a mixed state into a pure state. But how about nonlinearity? So the whole idea is, can I use nonlinearity to do, say, something like beam combiners, something else? It turns out that our systems, being microcanonical, when I start increasing the power, if I know how to excite the system so as to place it at a very low temperatures, optical temperatures, most of the power drops rapidly into the fundamental mode. So essentially, the nonlinearity will do all the dirty work for you without any phase locking mechanism. And what is amazing is that the fluctuations here subside. It's a peculiarity of the microcanonical ensembles at very low temperature. So essentially, they go from exponential. This is something Professor Macris proved many years ago that comes from the grand canonical. But eventually, at very low temperatures, you see the fluctuations of the fundamental mode become sharply Lorentzian. And as a result, the system exhibits high coherence. It can, as I said, it's like taking a mixed state into a pure state. So these are experimental results with two incoherent sources, two sources sharing 50-50 power, but mutually incoherent. And then you see, because of thermalization, you get something like 82% of the power in the fundamental mode, with the rest remaining in the second and the rest. And what is very interesting is that you get this purification, in spite of the fact that optically the entropy went up. So this is exactly what we see in experiments. This is from Professor Ajafigan's group. We see precisely what I was telling you with minimum fluctuations, in the fundamental mode itself. Again, these are also the same results along the same lines. Well, there are also some other aspects that are actually of intriguing to us. Is there any way I can see phase transitions? What I described so far is the thermodynamics of diluted optical gases. These are systems weakly nonlinear. But what happens if I increase the power, in which case systems become highly nonlinear, and as a result, perhaps coherent structures like solitrons come along? It turns out that solitrons, something that we have studied for many years, represent another phase. It's like solids. So essentially, you may get, if you run together a gas together with a solitron, right? A perfect solitron will be like, a solid at zero temperature. If the gas is very hot, it will evaporate the solitron, and what you are going to get is gas. Once, say, the energy components are resettled. On the other hand, if the temperature of a gas is low, this solitron being cool, it may actually condense the gas into another solid. So two solitrons really come along. So you see right away the prospect of phase transitions using this, all optical phase transition uses these aspects. Another component will be, what will be if we study, for example, frequency conversion processes. In optics, these are extremely important. Why? Because this is how we build parametric oscillators. And parametric oscillators typically require power. And the only way you can get power is to have multi-mode, big systems with a multi-mode. But then if they're multi-mode, if you don't know what you're doing, then you may not get the preferred outcome. It turns out that whenever we are dealing, say, with multi-frequency conversion processes, this is a paper we published very recently, these effects very much evolve like chemical reactions, no different than chemical reactions. So essentially, let me consider, for example, a four-way mixing process, a degenerate four-way mixing process, say in a fiber or any other system, multi-mode system.
So essentially, 2 photons at omega A provide you with 2 photons at omega B and omega C. This is no different if you analyze it within our framework than this, say, chemical reaction. Say H2, say hydrogen plus iodine will give you hydrogen iodide. So, and what is very interesting is that this stoichiometry that you see these twos, they come along in the conversion processes. So this is actually very intriguing in the sense that I may be able to describe something extremely complex. All these frequencies dancing around. Say frequency here may be supported by 800 modes, this 400, the other one 600. Highly chaotic, and yet you can predict them. So essentially the way you do it is you write down your Manley-Rowe relations, which are conservation laws, and then all together you maximize again the photonic entropy as you expect from the second law. And then something beautiful comes along. The power in frequency K, K, mode I, is given again by Rayleigh genes. So all the products and reactants share the same temperature, however, different chemical potentials. And interestingly, the chemical potentials reflect the stoichiometry of your optical chemical reaction. 2 mu A is mu B plus mu C. It's the same thing here. If you study chemistry, it will be the chemical potential of this product is the sum of the two times this chemical potential. Once you have that, now you can predict everything. You can say how this thing will unfold after arbitrary initial conditions. Even the numerics confirm this, right? These are brute force numerics that may take a couple of days, and yet they support these simple, say, relationships. But more importantly is now you have a tool to tell this is the way I have to excite the system to get the maximum second harmonic in the first mode of the second harmonic. Only then will be, of course, useful. And this is what it is, in spite of the fact that we are dealing with modes, highly multi-mode systems, involving hundreds of modes for the matter. Finally, let me say a few things about this thermodynamic optical pressure. It took us years to really understand what the p-hat what the p-hat is supposed to be. You see, if you study thermodynamics, you know that for every extensive variable, there is a conjugate intensive. So the mathematics demand, right, that if I take the partial of the entropy with respect to the number of modes, something should show up. But what this is, it was unknown at the time. It turns out that that p-hat is related to the actual electrodynamic pressure. Once you subtract this universal entropic term that comes along because the modes are discrete. You see, it's an irreversibility because the mode is discrete. So, by the way, getting this term is trivial. You see, p-hat over T is simply entropy over m-1, right? So just subtract this, you get electrodynamic, say, pressure. Now, what is fascinating is that we went there, we had 8,000 modes in a fiber. We obtained the electrodynamic pressure using the Maxwell stress method. To do that, you have to solve for 8,000 modes electromagnetically for all 6 electric field components, integrate over the surface, sum them up, and so on and so forth. This by itself, it took the graduate student I had, who is on, something like a month to put the program together. On the other hand, if you use this comes in a second, and you cannot tell the difference between the two. What is very interesting, however, is that when you compute the optical pressure thermodynamically, not electrodynamically, you don't need to even know the electromagnetic field structure of the modes. In other words, if you never took a course in electrodynamics, even if you don't know what is E and H, you are still going to get this thermodynamically. I find this amazing. The next topic is to see if there is a way to see thermalization dynamics in quantum systems. So we are targeting, say, superconducting platforms. This is something we're pursuing together with our colleagues at USC. And the whole idea is to see whether we can actually see the interface of quantum and classical, right, in these, arrangements. In any event, there are several aspects that are really interesting that we're currently pursuing. I hope by the end of this talk, I may have been able to really convince you what you are looking at. It's a new, aspect, a new framework within the area of optics and photonics with no counterpart before. And of course, before I close my talk, I would like to thank, besides my colleagues, my postdocs, Yorgos Piriallakos, my student Mahmoud, Huizong Ren, Eddie, and Abraham. These are students of Mercedes. And with that, I would like to congratulate again Dr. Οικονόμου for this important milestone in his life. Thank you so much.
Thank you very much for such an inspiring talk. We have time for questions.
Yes, Dimitri. Yes.
I understand that the system is somehow thermalized, right?
Yes.
So in an actual system, this means we can work in CW, but what will happen if we try to work with pulses?
Well, if you go with femtosecond pulses, you're going to run in trouble. Nevertheless, a lot of these systems work in CW, never mind using nanosecond pulses. Thermalization typically is observed in our systems within a couple of meters. So if we have a pulses, say, of 300 picoseconds, and so on, dispersion or anything else is insignificant. It will be an issue if we go down to, say, 500 femtoseconds, 400 femtoseconds, and so on. But these are never used really for beam combining, as you know very well. All right.
Thank you.
All right.
Okay, if we don't have other questions, let's thank our speaker again.
Thank you.
Thank you very much. Let's move on to the second talk of the session by Professor Efthymios Kaxiras from Harvard University. That he's going to talk about the electrons and plasmons into delayed materials. Thank you very much for accepting our invitation. The floor is yours.
Thank you very much for the introduction, and I'd like to, this is it. Yeah, Efthymios. Okay, and I'd like to mention that all the credit for the organization of this event goes to Kostas and Maria and Spiros. They've done everything, and I'm very happy to be part of it. We are celebrating Professor Οικονόμου's 85th birthday, and we've heard a lot about his research accomplishments, which are quite extraordinary. They cover four broad areas: electrons in solids, elastic waves, electromagnetic waves, and metamaterials. I want to say a few things with a more personal view of Professor Οικονόμου's contributions. I met him about 30 years ago when I started teaching at the summer physics schools organized by him and his colleagues at the physics department here at the University of Crete. He's been my role model ever since. He has influenced me very strongly in my outlook, in my understanding of physics, in my decisions. I thank him very much for that. And I think it's entirely appropriate that we pay tribute to him for all these contributions. One of the wonderful things that I learned from him early on in the mid-90s, by participating in the physics summer schools was that you really need to focus on extracting the essence of physical behavior. Maria made some similar comments in the morning session, and trying to understand orders of magnitude rather than the details, and the general origin of different phases of or regimes of physical behavior. And through this kind of fundamental approach, I think what he has done has made a huge difference in physics and in our understanding of interesting complex phenomena. Now, these days, as Spiros also mentioned in the morning, we can quantify things with statements like the one I just made with data. So here's some quantification of Professor Οικονόμου's contributions. So this is a plot of from the Web of Science for his publications and citations, and in the spirit of orders of magnitude and phases, his contributions through these 6 decades approximately, zeroth order, have been of order of magnitude 10 papers per year, which is quite extraordinary, maintained over 6 decades. And citations were originally going up at a very healthy pace, and at some point the world discovered the importance of his great paper on plasmons, as Maria pointed out in the morning, so it shifted to a very much higher rate of citations, which is really wonderful. And before I talk to you about my research and connections that it has and inspirations from Professor Οικονόμου's work, I wanted to spend a few minutes highlighting some of his contributions beyond research. Those were mentioned in the morning session also, but most of this was in Greek, so I'd like to share with you the same general comments, but in English and from a personal perspective. So he's made really amazing contributions in administration and policy, in service to science, and also in book writing. So for his contributions to science, administration, and policy, this is the front page, this short description button in the web page of Forth. And it's an amazing institution for Greek standards. It's by all measures the preeminent research organization in Greece in number of researchers, in number of papers published, in grants that it attracts, and so on. I'm not going to go into the numbers. You can easily find those on the web. And it contains 10 institutes spread over 8 different cities in Greece. In early 2000, I spent a few years on leave from Harvard at my home city in Ioannina. And at that time, I served as the director of one of these institutes, which was at the time, and I think it still is, the smallest one of the 4 institutes, the Institute for Biomedical Research. And at that time, it had 1 permanent researcher and about half a dozen of affiliated faculty. And it took me a lot of time to manage that institute. So especially because of the peculiarities of doing research in Greece and providing for the needs of a research institute. I use the word peculiarities, so I don't use a stronger term. And you can imagine how this extends to an organization with thousands of researchers and spread over 8 cities. And if you click on another button on this website, on the former presidents, here's the list, starting with Professor Οικονόμου, who served for 21 years from the inception of this organization to its maturity. So this really was an extraordinary contribution to science in Greece and Europe more generally. I want to also say a few words about his record in book publishing, which is also, in my view, quite amazing. So this is the list of all his books that my friends at the Crete University Press helped me put together. because that's the publishing house with which he published most of his books. There's a few more books from other publishers. So here's a list of the titles. All the titles here are in Greek, except for one item. So I translated all the titles here. So it starts with Nuclear Weapons and Human Civilization. Physics Today, volumes 1 and 2. Statistical Physics and Thermodynamics. Physics of Solids, volumes 1 and 2. From Quarks to the Universe. Solid State Physics. Our World, the Tiny, the Great, according to physics. Science, Where Has Thy Glamour Withered? And the Physics of Solids, Essentials and Beyond. Green's Functions in Quantum Physics. Now, some of the titles, I took some liberty in translating them. The titles are actually quite beautiful in Greek. They come from, or they evoke lines from famous poems or lines from the liturgy in the Greek Orthodox Church. I hope I did justice to translating them. And they really are a wonderful contribution, a total of 12 volumes over roughly 60 years, one volume per 5 years. That's quite incredible as well. And I haven't read them all, I confess, but my favorites are, of course, Green's Functions in Quantum Physics. I've learned a tremendous amount of physics from this. It was already mentioned by several people. And Maria, I believe, paid some tribute to this wonderful book. And the other two that I particularly like are this one. This is The Physics of Solids, Volume 1. I taught from this book when I was at the faculty at the University of Ioannina. At that time, this was a new department in material science and engineering. That was the competing department from the one that Lefteris helped establish at the University of Crete. And it was a wonderful experience to teach from this book. It's incredibly lucid and clear, and both I and the students enjoyed that tremendously. One particular thing that I learned from this book is the importance of the tight binding approximation, both as a conceptual tool as well as a computational tool. And last but not least, this beautiful little book, From Quarks to the Universe. And this book has been used by Professor Οικονόμου to teach an introductory physics course to the physics students at the University of Crete. And just in case you think this is kind of physics of poets, light introduction, it is not. It is actually quite demanding. So here's one page from the book on the strong interaction, full of Feynman diagrams. And just in case you think this is the use of Feynman diagrams, but still not really in a deep way, here's a bunch of exercises at the end of this chapter with assignments to figure out what is going on in terms of Feynman diagrams. So it really is a very serious physics book used to introduce physics students to the wonderful world of physics, covering essentially all the possible interesting topics in physics. So, so much about research, administration, and policy and books. I'll switch gears now and tell you a little bit about work that we have done in my group in the last few years. And I'll focus mostly on work that touches on subjects or has some relation, at least, to things that Professor Οικονόμου has dealt with in his career. So the title of my technical presentation is Electrons and Plasmons in Two-Dimensional Materials. We have been focusing on two-dimensional materials for the last about a little over 10 years now, 10 to 12 years. And a representative solid, two-dimensional solid is graphene. Plasmon, of course, is a quantum of electronic charge oscillations, and plasmons in graphene show a lot of very interesting and unique features. Of course, they are confined in two dimensions because graphene is a single plane of carbon atoms, and therefore their electromagnetic energy is also confined there. There's the possibility of having ultra subwave length plasmons excited in graphene, and there's also the possibility of tuning them, the tunability of their frequency by doping, by changing the number of available electrons. So here's a simple illustration of a plasmon in graphene with the oscillations of the electromagnetic field. And the one thing that I wanted to highlight, this kind of picture was shown earlier in previous talks. So this is the decay length of the field going away from the plane of the atoms, and Xi is an important parameter in this system, half of the decay length. So what's so special about graphene? Why is it an interesting and peculiar solid in many ways? It's because the combination of the two-dimensional honeycomb lattice of carbon atoms and the orbitals, the atomic orbitals associated with each one of those atoms make for a very interesting band structure. So here's the band structure of graphene with all the states, but of course the most interesting ones are the ones close to the zero of the energy scale, which is the Fermi level. So that's the charge neutrality point when graphene is neutral, the position of the Fermi level for neutral graphene. And the combination of those two features produces this very interesting, strange, unique behavior that is massless electrons, electrons in which the energy is proportional to the momentum rather than the momentum square. So those are referred to as massless electrons, and their behavior near these points, which are the K points of the hexagonal Brillouin zone, are referred to as Dirac cones. These features give graphene very special behavior, so very, very high mobility for freestanding graphene, 200,000 in these units, whereas typical mobilities in solids are of order 1,000. So this is 200 times higher than typical solids. And of course, you can get all this behavior from a first neighbor, tight binding Hamiltonian, as emphasized in Professor Ekonomu's wonderful solid state physics book, with one orbital per atom. If you want more details, you can go beyond that simple approximation, but that gives you the essence of the physics. So what can you expect when you have when you excite plasmons in such a system? Well, it's all contained here, basically. This paper was mentioned several times already in previous talks. So this is, I believe, directly from the PhD thesis of Professor Ekonomu, published in 1969, June 10th, almost close to the date we have today. And these are a couple of pages that show different types of physical systems, and you can see here a metal surface, an insulator, and then another metal surface, and so on. So a very interesting geometric arrangement. Another geometric arrangement with more metal surfaces and insulating regions between them, and so on. And beautiful analytical results here, the description of what you would expect for the frequency of the plasmons as a function of wave vector for these types of systems. So the question that we posed is, what if you took graphene to be the metal, which is the thinnest possible metallic structure, and you interspersed this dielectric material with other two-dimensional solids, again, giving you perfect flatness with the appropriate dielectric constant. So you might be able to put together a structure like this with periodic graphene layers. So these are the conducting layers separated by a distance d. And then you could ask, in this periodic structure, what are the allowable propagating electromagnetic modes, and what are the bands that they form? And could this be used to design metamaterials with desirable effective permittivity? Let me point out that the quantity Xi that I mentioned earlier, that is characteristic of the decay length, has this relationship with the plasmon wave number and the dielectric material wave number and its dielectric constant. So we have a system with anisotropic uniaxial dielectric as the host medium, 2D metallic layer characterized by the conductivity of graphene, and plasmons excited with both Kz plasmon along the plane direction and Bloch Kx wave numbers. X is the direction perpendicular to the layers. We could do some analytical work. This is actually the work by Marios Mattheakis, a student who got his PhD from the University of Crete and then came to my group as a postdoc. We analyzed the system. I'm not going to go into the details, just to point out that there are three different distinct regimes of behavior. The first one is when the periodicity of the structure is greater than this length scale Xi, and then you get the weak plasmon coupling and elliptical bands. When D is equal to Xi, you get a critical plasmon coupling and two linear bands with this relationship between Kz, the plasmon, and the Bloch wave numbers. And when D is smaller than Xi, you get strong plasmon coupling and hyperbolic bands. And this is a very interesting case referred to as plasmonic Dirac point. So here are the relationships between Kx and Kz, normalized by K0, the dielectric wave number. And this is the regime where Xi is less than D, the periodicity of the structure. The regime, the case where Xi equals D, and the regime where Xi is greater than D. When Xi is equal to D, you get these two dashed lines in this plot where there's the so-called plasmonic Dirac point. The two lines intersect here, and the dispersion is linear, very close to this point. And if you go to values of D greater than Xi or smaller than Xi, there's a gap that opens and the behavior becomes parabolic or hyperbolic. Interestingly, Marios did also extensive simulations to see what happens. So here we have a two-dimensional magnetic dipole source, the little white dot. And from this dot, spherical waves emanate, and you see how they propagate. We took a few parameters here for the spacing of the graphene layers, the dielectric, the anisotropic dielectric medium, and so on, and calculated the propagation. And in the plasmonic Dirac point, you have epsilon near zero, essentially zero dielectric constant, and this is shown, the behavior is shown here from computational simulations. In the weak plasmon coupling, you have normal refraction, and again, this is how the waves spherical waves that emanate from the source propagate through this region. The black region, by the way, is this periodic arrangement of the graphene layers separated by the dielectric. And finally, in the strong plasmon coupling regime, you get this negative refraction result. We've heard some of this in earlier talks about the importance of negative values of epsilon. And you can then talk about how can you explore the parameter space in the system. For example, for different values of D, the separation between graphene layers, how can you play with the chemical potential of the electrons and the wavelength to achieve epsilon near zero behavior. The lines here are epsilon near zero behavior. This blue dashed line corresponds to the D equals 20 nanometer separation. And you can also plot the values of the real part of the effective dielectric constant or the imaginary part of the effective dielectric constant as functions of the chemical potential of the electrons and the wavelength. And the dashed lines here, black and white, are the epsilon near zero points. And you can get behavior which has very large negative values. But this corresponds also to high losses. And you can play with this to create very, very interesting material systems with this type of behavior. One question that you might have, okay, I can easily change the wavelength of light, but what about the chemical potential? Can I tune that over a range of values of 1 electron volt? Well, it turns out that graphene has this special layered nature, of course. Graphene is a single plane of atoms, but you can stack a few planes of those atoms and intercalate them, put other atoms in between. And these intercalation atoms can provide extra electrons to dope graphene. Here's the band structure again of a two-layer graphene system with lithium as intercalant. This raises the Fermi level from 0 to a little bit above 1. You can even make it higher, the chemical potential, by 3 layers of graphene with 2 layers of intercalated lithium and so on. Intercalating lithium in graphene, by the way, is very simple. That's how all the lithium-ion batteries work. So it's a very common process. You can play with these parameters a lot and get all sorts of interesting results. Let me just highlight one of our results. Let's just focus on the middle panel here, which shows the behavior of the plasmon frequency, the plasmon modes, as a function of wave number. And you see this characteristic behavior very much like it was predicted in the article from almost 60 years ago by Professor Οικονόμου for these very interesting arrangements now taken to the limit of ultra-thin metallic layers. And you can tune them so that the optical range highlighted here in yellow has reasonable losses and reasonable ratio of reasonable localization and reasonable losses that's characterized by the ratio of the wavelength in air versus the plasmon wavelength. Okay, I'm going to switch gears again and go to a different topic, which is the one that I've been working on in the last decade very intensively. And this has to do with two-dimensional materials with a twist. So you take 2 layers of these materials, like graphene or similar layered materials, and you put 1 layer on top of each other, but with a small twist, relative twist. And this gives rise to all sorts of amazing new possibilities. The reason is that the twist produces a new length scale, the so-called Moiré length scale, which is a pattern with a much larger periodicity than the atomic length scale. And this new length scale, the Moiré length scale, then produces all sorts of interesting behavior for the electrons, which now must obey both the atomic scale periodicity of each layer and the large length scale periodicity of the imposed pattern by the twist, relative twist of the 2 layers. And here's a list of very exciting applications: quantum magnets, superconductors, magnetic 2D layers, Floquet and cavity engineering, Kitaev models, Majorana zero mode, and so on. Here's another list of actually observed phenomena in these types of systems, which is very impressive. Correlated insulator behavior, superconductivity, orbital ferromagnetism, strange metal behavior, chair insulating states, pneumaticity, fractional churn insulators, fractional quantum anomalous Hall effect, Wigner crystals, and so on, just by simply introducing the twist between a few layers of these systems. Why is all this happening? Well, here's a geometric representation of a twisted bilayer graphene. You see the 2 graphene honeycomb lattices superimposed. And this superposition with the twist produces different regions in the system labeled as A, B, or BA. Those are equivalent by symmetry, or AA. The AA regions correspond to the 2 layers exactly on top of each other. So the top layer hides completely the atoms in the bottom layer. The AB or BA regions correspond to the top layer atoms, the orange ones, hiding only half of the atoms in the bottom layer. So this is the AB or BA arrangement. It turns out that this is the low energy arrangement, and this is the high energy arrangement. So this is what the system doesn't like. And these triangles are what the system likes as local geometry. And this competition produces very interesting effects in itself. So this is quite a complicated system from a structural point of view. It has a triangular lattice of these AA regions. It has a honeycomb lattice with two bases atoms, in quotes, the AB and BA regions, and it has a Kagome lattice of the blue domain walls separating the AB from BA regions. Now, in this system, you can think of it in a sense as a very deliberate arrangement of defects, very much in the spirit that was mentioned earlier, the defects being the AA regions where the system doesn't like to be. And because of these defects, you get localization of electrons. So this is a beautiful case of how you can induce electron localization due to a very deliberate arrangement of defects. And this was known quite early on, from around 2010, 2012, both from theoretical considerations and from experimental measurements. And here's a plot of the density of electrons in real space. And you see these very large peaks that correspond to the AA regions. So you do get indeed electron localization because of this. Now, there's a beautiful theory that was developed by Alan McDonald and collaborators from the University of Texas. This is the reference, where they analyzed this system in terms of the supercell Brillouin zone. Each graphene contributes its own Brillouin zone, a hexagonal shape, the red one for the first layer and the blue one for the second layer. And the supercell created by this superposition is the black Brillouin zone. And at the corners of these Brillouin zones, you get a set of Dirac cones that I mentioned earlier from each layer. Now, these Dirac cones at some points interact, and where the Dirac cones interact, then they split to bonding, anti-bonding states, and this splitting produces flat bands. And it is these flat bands that play a dominant role in the behavior, the physical behavior of the system. The flat bands produce density of states, which is much, much higher by almost a factor of 1,000 compared to what the simple graphene layer would have. So we're talking about huge enhancement of the density of states, and this flatness of the bands produces the localized behavior. Now, McDonald proposed this very simple Hamiltonian. The diagonal terms describe the contributions of each graphene layer separately. The off-diagonal terms describe the coupling of the two layers, and based on this, he could predict a lot of the behavior of the system. We like to do things from ab initio perspective, really having all the atoms there and detailed calculations to get the behavior of the system under different conditions and have full control of what is going on. So we put a lot of effort in producing an ab initio tight binding Hamiltonian in the spirit that I was mentioning earlier, having realized the importance of this kind of approach for both conceptual and computational reasons. And when you do this, the appropriate localized bases, localized orbitals that capture the behavior of this more complicated system is shown here. It contains as the zero angular momentum component the simple pz orbital of each carbon atom, but also higher angular momentum components. And with this theory, we were able to do detailed calculations as a function of twist angle and, of course, the energy for the density of states. And you see this huge enhancement of the density of states for a twist angle of about 1 degree or so. Very much what experiment sees, but then full-blown atomistic calculation. And I had a video to show you this. When you transfer a talk from a Mac machine to a PC, the videos never work. Okay, so be it. This is a schematic of the flat bands again, near the so-called magic angle, and the huge enhancement of density of states, the blue line here of the bilayer, the twisted bilayer, relative to the pure graphene layers, enhanced by a factor of 1,000. So all these effects are very, very interesting and nice. About 7 years ago, Pablo Jarillo Herrero and his group at MIT took this system and put it under the right conditions of temperature and discovered that it is a superconductor. So this is current, and this is the voltage drop. And for a certain range of current values, no voltage drop, a true superconducting behavior once the temperature falls below 1 degree or so. So these papers now have attracted a lot of attention and have really exploded the field in terms of interest. And the detailed calculations that my student Shang Fang had done helped guide experimental searches for this wonderful discovery. Now, this is the plot that many people show related to this system. This is again from Pablo Jarillo Herrero's group, and you can think of this, oops, sorry about this, pressed the wrong button. So you can think of this vertical axis as the density of states, and the horizontal axis as the energy position, the position of the Fermi energy. And as you scan the position of the Fermi energy, you see these different density of states. Now, the black dashed lines is what you would expect from single particle bands from the theory that I was just describing. What you see in experiment is very different, with sub-bands and mini gaps separating these sub-bands. And of course, this cannot be explained in terms of the single particle picture. You need a many body, many particle picture, something like the Hubbard model shown here in terms of the kinetic energy and the on-site repulsion between electrons. This is something beyond the kind of theory that I was showing you earlier. But in order to construct a proper Hubbard model type of description of the system, you need to know where the electrons go and what are the relevant states and so on. So here's a plot of the displacement field of the atoms, how the atoms relax in these structures, both in plane relaxation and out of plane relaxation. You can see that this is quite complicated. This is a schematic representation of it. So the actual structure looks like it has small hexagons in the middle, separated by these domain walls, and then large triangles. Those are the A, B, BA regions that I was mentioning earlier. And all this is a very complicated lattice on which to try to solve the Hubbard model. It's actually almost out of reach. And if you ask the question of what do the wave functions of the electrons look like, so these are typical electronic wave functions associated with the flat bands that I'm showing you here, projected in different bands. And you see that some of them are near the AA regions here. Some of them are in the domain walls. Some of them are in the triangular regions and so on. Very complicated system. Very recently, we've been able to do fully ab initio calculations. Here's the number of atoms involved in different twist angles, ranging from about 3.5 degrees all the way to less than 1 degree of twist. Those are very large systems containing of order 10 to 15,000 atoms. And we can identify the wave functions of different points in K-space, analyze them in great detail, where they come from, what are their special features. I'm not going to get into the details, but just to give you a sense that this kind of detailed calculation now allows us to do with these electronic wave functions at different points, these types of integrals, which are the Coulomb integrals representing the electron-electron repulsion at different lattice sites, and slowly built a Hubbard-type model for this complex system. So this is where we are with this type of work. And we've done a bunch of other things in two-dimensional materials, twisted bilayer graphene, tri-layer graphene, quadrilayer graphene. This is becoming very fashionable. 5 layers have the highest superconducting temperature at the moment, and there's a lot of interesting possibilities there. We've done calculations for phonons, transition metal dichalcogenides, other types of systems, including excitons, systems with ferroelectricity, and so on, and modeling with machine learning tools. I don't have time to get into that. I just want to give you one very quick example that actually of a system that comes back to things that were mentioned earlier. This is a different type of system, hexagonal boron nitride. Again, it comes, it's a layered system, layers of boron and nitrogen atoms. So boron is blue, nitrogen is green, and you can think of these types of stackings, A, B, or BA, just like in graphene. But now you notice that the different type of stackings produce polarization because of charge transfer. So this stacking corresponds to a polarization vector pointing in this direction. This stacking, which is equivalent by symmetry, points to a polarization vector that points, produces polarization that points in exactly the opposite direction. Now, with these types of detailed calculations, with electronic wave functions, we can do the calculations that give us a quantitative description of the polarization, and we can predict what is happening in these systems. And here's what's happening. So this is the twisted boron nitride system here in the middle. Imagine now, and as I already mentioned, the different domains, because of the twist in the system, the A, B, or BA domains will produce different polarizations. Imagine now that you put graphene on top of this twisted boron nitride layers, and the different polarization will shift the chemical potential, the Fermi level of graphene. And the moire domains will be then experienced by these graphene Dirac cones, and this will modulate the plasmonic response, coming full circle back to plasmonic behavior. And this is exactly what was done in experiment. We were actually collaborating with this experimental group to provide the theoretical justification for what they see. And this is basically what they see. They see different domains in the system monitored by different polar domains in this twisted bilayer of boron nitride, monitored by the plasmons excited on the graphene layers that encapsulate this twisted bilayer system. So this is another example of more complicated systems than graphene, where again, you can use graphene, you can use plasmons and do all sorts of really neat experimental designs. Hopefully, some of them can even be implemented in real devices. I showed pictures of several members of the group as I was going along. Here's a picture of a bunch of them that contributed to the more recent work that I have been describing. Most of them have moved on to other jobs already. And this is the acknowledgements of the funding. And this is my very last slide. But in my very last slide, I will not congratulate Professor Οικονόμου on his 85th birthday. And the reason is that he has told me many wise things in the 30 plus years that I know him. And one of the wise things that he has told me is it makes no sense to congratulate someone on his or her birthday. This is time will just bring that. So instead, I will just wish him a very happy birthday and many, many more happy birthdays. And I want to extend to him heartfelt thanks for all the amazing contributions that he has made during the past six decades of his active scientific life. Thank you, Eleftherios.
Thank you very much for such an exciting talk. To have maybe time for one question. Do you have any questions? Okay, so if not, let's thank our speaker again. So now, so far we're seeing talks. Now we're going to hear a talk, right? So there's a music event by Mr. Aris Sfakianakis. So who's we're going to see him now. So let me say a few words. Aris Sfakianakis is a lyrical singer and a choir conductor. He was born in Heraklion, here in Crete, right? And studied in Greece and at the Royal Academy of Music in Ireland. So he has collaborated with Greek National Opera and the Earth Channel, right? And the mixed choir of Municipality of Athens. So we're happy to host him, right? And we're happy to hear him as well. So Let's enjoy.
Καλή μου ξανθιά, συντροφιά μου γλυκιά, που μαζί σου λαλώ κάθε ωραίο σκοπό. Ήρθες εφάνεις, με σουράβλη να εφάνεις, ύμνους και λαϊδισμούς, ήχους αερινούς. Ήρθες εφάνεις, με σουράβλη να εφάνεις, ύμνους και λαϊδισμούς, ήχους αερινούς εμπρός αρχή να πες τους γλυκά, τους αναπέστους εμπρός αρχή να πες τους γλυκά, τους αναπέστους. Ω καλή μου ξανθιά, συντροφιά μου γλυκιά, που μαζί σου λαλώ κάθε ωραίο σκοπό. Ήρθες εφάνεις, με σουράβλη να εφάνεις, ύμνους και λαϊδισμούς, ήχους αερινούς. Ήρθες εφάνεις, με σουράβλη να εφάνεις, ύμνους και λαϊδισμούς, ήχους αερινούς εμπρός αρχή να πες τους γλυκά, τους αναπέστους εμπρός αρχή να πες τους γλυκά, τους αναπέστους. Τα αστέρι του βοριά θα φέρει ξαστεριά, μα πριν φανεί μέσα απ' το πέλαγο πανί, θα γίνω κύμα και φωτιά, να σ' αγκαλιάσω ξενιτιά. Κι εσύ, χαμένη μου πατρίδα μακρινή, θα μείνεις φάδι και πληγή, σαν ξημερώσεις άλλη. Τώρα πετώ για τη ζωή το πανηγύρι. Τώρα πετώ για της χαράς μου τη γιορτή. Πεγκάρια μου παλιά, καινούρια μου πουλιά, διώχτε τον ήλιο και τη μέρα απ' το βουνό, για να με δείτε να περνώ σαν αστραπή στον ουρανό. Τώρα πετώ για τη ζωή στο πανηγύρι. Τώρα πετώ για της χαράς μου τη γιορτή.
Okay.
Τώρα που πας στην ξενιτιά πουλί, θα γίνω του νότια, γρήγορα να σ' ανταμώσω. Για να σου φέρω το σταυρό που μου παράγγειλες να βρω, δάχτυλίδι να σου δώσω. Ήσουν κι η Παρίσι στην αυλή μου αγαπημένο, ποιος θα μου χαρίσει το φιλί που περιμένω, στο μόρφο ακρογιάλι καρτερό να μου έρθεις πάλι, σαν μικρό χαρούμενο πουλί. Ήσουν κι η Παρίσι στην αυλή μου αγαπημένο, ποιος θα μου χαρίσει το φιλί που περιμένω, στο μόρφο ακρογιάλι καρτερό να μου έρθεις πάλι, σαν μικρό χαρούμενο πουλί. Εσύ μου αγάπη έχε για να ναι μαζί σου Παναγιά, κι όταν έρθει το περιστέρι θα έχω κρεμάσει φυλακτό στο παραθύρι τ' ανοιχτό, την καρδιά μου σαν αστέρι. Ήσουν κι η Παρίσι στην αυλή μου αγαπημένο, ποιος θα μου χαρίσει το φιλί που περιμένω, στο μοκρανιάλι καρτερό να μου έρθεις πάλι, σαν μικρό χαρούμενο πουλί. Ήσουν κι η Παρίσι στην αυλή μου αγαπημένο, ποιος θα μου χαρίσει το φιλί που περιμένω, στο μόρφο ακρογιάλι καρτερό να μου έρθεις πάλι, σαν μικρό χαρούμενο πουλί. Μια πολύ μαγική, ζούμε μαζί κι οι δυο αγαπημένοι. Μια πόλη σαν κι αυτή πεθαίνει, ζει κι αλλάζει μαγεμένη. Σαν πέσει σκοτεινιά η αναπνοή μου ας μίξει με τα γέρη. Τότε η πόλη θα φανεί μονάχα ερημική, σαν τα κρύβω μου αστέρι. Σαν πέσει σκοτεινιά η αναπνοή μου ας μίξει με τα γέρη. Τότε η πόλη θα φανεί μονάχα ερημική, σαν τα κρύβω μου αστέρι. Ζητάς αθανασία στο μπαλκόνι μου μπροστά, δε μου δίνει σημασία κι η καρδιά σου πως βαστά. Σ' αγάπησανε στον κόσμο βασιλιάδες ποιητές κι ένα κλωναράκι δυόσμο δεν τους χάρισες ποτέ. Είσαι σκληρή σαν του θανάτου τη γροθιά, μα ήρθαν καιροί που σε πιστέψαμε βαθιά. Κάθε γενιά δική της θέλει να γεννείς, ορφωνιά που δε σε κέρδισε κανείς. Ή ζητάς αθανασία στο μπαλκόνι μου μπροστά, ποια παράξενη θυσία η ζωή να σου χρωστά. Ήρθαν διψασμένη κρίση, ταπεινοί προσκυνήτες κι απ' του κήπου σου τη βρύση δεν τους δρόσισες ποτέ. Είσαι σκληρή σαν του θανάτου τη γροθιά, μα ήρθαν καιροί που σε πιστέψαμε βαθιά. Κάθε γενιά δική της θέλει να γεννείς, ομορφωνιά που δε σε κέρδισε κανείς. Thank you. Είχα φυτέψει μια πορτοκαλιά που την ζήλευε όλη η γειτονιά, που την ζήλευε όλη η γειτονιά. Είχα φυτέψει μια πορτοκαλιά. Αχ, Μαργαρίτα, Αγιοπούλα, αχ, Μαργαρίτα, Αγιοπούλα, αχ, Μαργαρίτα, μάγισσα. Πρωί-πρωί την πρώτησα φιλιά, το δειλινό την πήραν τα πουλιά, το δειλινό την πήραν τα πουλιά. Πρωί ρωτήσα φιλιά, αχ, Μαργαρίτα, Αγιοπούλα, αχ, Μαργαρίτα, Αγιοπούλα, αχ, Μαργαρίτα, μάγισσα. Στο κεριγιάλι το κρυφό κι άσπρο σαν περιστέρι, διψάσαμε το μεσημέρι, μα το νερό γλύφει. Διψάσαμε το μεσημέρι, μα το νερό γλύφει. Πάνω στην άμμο την Ξάνθη, γράψαμε το όνομα της. Ωραία που φύσηξε ο πάτης και σβήστηκε η γραφή. Ωραία που φύσηξε ο πάτης και σβήστηκε η γραφή. Με την καρδιά, με την πνοή, την πόθους και την πάθος, πήραμε τη ζωή μας. Λάθος κι αλλάξαμε ζωή. Πήραμε τη ζωή μας. Λάθος κι αλλάξαμε ζωή. Senza di te languisce il cor. Caro mio ben, senza di te languisce il cor. Il tuo fedel aspirayor, cesa crudel tanto rigor, cesa crudel tanto rigor, tanto rigor. Caro mio bene, un'aria serena dopo una tempesta, bell'aria fresca pareggia una festa. Che bella cosa una giornata e sole, manna tu sole, più bello in me, oh sole mio, sta in fronte a te, oh sole mio, sta in fronte a te, sta in fronte a te. Quando fa notte, sole se ne scende, me viene quasi una malinconia. Sotto a finestra tu a restaria, quando fa notte sole se ne scende, manna tu sole, più bello in me, oh sole mio, in fronte a te, oh sole mio, sta in fronte a te, sta in fronte a te.
Thank you. Ευχαριστώ.
I suggested to the organizers that we must have finished with this beautiful musical event, and there was no any need for me to say anything, but Spiros is very strict, so said that was the announced program and we'll stick to this. Of course, the first thing to say is that my very warm thanks to all speakers for their very generous presentation of my contribution, both local and from all over the world. In the written text I have prepared, I was thinking of stop at this, but after I listened to all this talk, I found them very excited and very enjoyed. And I would like to say that, you see, that I was not expecting to be so good. As a matter of fact, I was thinking of asking for your forgiveness for having you so many hours. I felt uncomfortable to spend. When Maria and Spiros approached me with their proposal, for a moment I was thinking of saying no, but then I moved, you see, from this very touching thought of them, and I thought that I had no right to say no. So here we am, this one. But after all, at least to me, it turned much better than I was expecting, and I thank you all of you for that. Okay, I would like to make some very short remarks regarding my scientific works. First of all, my work on surface plasmons, that was my thesis work, was suggested to me by my thesis advisor, Morel Cohen, with the thought that this excitation may play a role analog to phonons, and thus mediate electron attraction and being helpful for superconductivity. As you have heard from Sergei, there were so many branches to this field, but none of them to superconductivity. This shows, you see, that it's very, very difficult to predict how things would develop. So, let me say also my most successful book about Green's functions in quantum physics. This book grew out of a series of lectures to computational physicists and to experimentalists, and I was not expecting to be a book, to be a successful book. It turned out this way. And I would say that I found sometime in a bookstore in Athens my book in the section for green energy because of the name. Also, I have to make a special mention also to my long and fruitful collaboration for over 40 years with my dear friend Kostas Soukoulis, who died last year at the age of 73. Kostas contributed significantly to my scientific output. Also, Kostas contributed significantly to the development of Ford for many years and to the creation and development of the Department of Material Science in this university, and I felt an obligation to make a notice about that. Now, after I returned to Greece, my scientific and other work was determined by external conditions because I was heavily involved with the management, first at the university for about 4 years, from 1980 to 86, and then to the creation of a new research center, that of Ford, from 83 to 2004, for about 20 years. Nevertheless, I found some time to teach and, as a side effect, to think about physics, its unique ideas, and its hidden simplicity. I discover also the power of dimensional analysis, which I think is an important subject that is not taught so much in the curriculum of the physics department. After all this thinking, teaching experience, I transfer a lot of this to my books, and you have heard enough about that to repeat here. Regarding my research, I will finish by saying that probably the most important contribution over these few 20 years or so was my contribution to the problem of waves in periodic, sound waves in periodic systems, and you have heard about that. Also, the last year I have to mention that I have found a new field that I'm to some extent active, and that was due to Kostas Makris, who was among the organizers in non-Hermitian problems. During my 50 years or so, there was no thought that could do anything else except Hermitian physics, because that's nature. But inventive minds find new directions and offer for us the opportunity to do something that is not quite trivial. I would like to thank all of you for spending so many probably uncomfortable hours in this room. And I have to repeat again my thanks to all of you. Thanks a lot. I should add that my contribution to Forten, to the University of Crete, was a predetermined way of action. It turned out with a Greek saying, this is what I would like to finish, το αγωγιάτι, το ξέχασα. Το αγώι κάνει τον αγωγιάτη. Αυτό happened to me, you see, in all these years. I have to explain this, that I will not say it in a proper words. I will not try to translate. Okay, thank you again.
So, So we thank Professor Οικονόμου. We thank Professor Οικονόμου with all our respect and our love. We organized this event, and we thank you all for being here. There is some wine and cheese upstairs for everybody, so please join Professor Οικονόμου and all our speakers for some wine and cheese. Thank you all. Θέλω να τις πάρω αυτές τις